Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe unwinds just slowly enough for you to drift with it. Tonight, we'll take a journey that's happening all around you, even as you sit still. You might think you're resting, maybe lying back, maybe holding a warm drink, but in truth you're already travelling. The floor beneath you is moving, the planet is turning, the sun is sailing through the galaxy, and you are part of it, an unknowing passenger on a ship of unimaginable size. Have you ever wondered how it feels to move without feeling it? To be carried through the dark on a vessel so vast that every sense you have swears you're standing still? That's where we begin tonight, with the quiet illusion of stillness and the reality hidden beneath it. Before we set off, if you find comfort in this calm exploration, if the thought of science whispering you to sleep feels like a good way to end your day, I'd be ever so grateful if you left a like or subscribed. It helps this little world of wonder reach others who might need a soft place to rest their thoughts too. Now, let's settle in. The world around you is moving and you're going to feel none of it, which is perhaps the most extraordinary thing of all. If you step outside and look up at the night sky, the stars seem peaceful, steady, fixed in place. They twinkle gently, but they don't drift or whirl. You might even imagine the whole sky as a great still dome and the earth as a calm platform resting beneath it. Yet the truth is almost the opposite. We are not at rest at all. The earth is in motion, several motions all at once, layered like the gears of a great cosmic clock. Every second of every day, you are hurtling through space at speeds that are almost impossible to imagine, and somehow it feels like nothing at all. It begins close to home with the simplest motion of all, the turning of the earth. The ground under you is spinning, turning from west to east, completing one full rotation roughly every 24 hours. At the equator, that means every person, tree and ocean wave is moving at about 1,770 kilometers per hour relative to Earth's axis. That's faster than the speed of sound. Even if you're not at the equator, you're still racing through space faster than any commercial jet could ever hope to fly. Yet you feel none of it because everything around you, including the air, the oceans and every atom in your body, shares that same smooth, steady spin. There's no wind of motion, no rush against your skin. Motion only makes itself known when something changes, when one thing moves differently than another. And on this great turning sphere, everything moves together. That rotation gives us the rhythm of day and night. It's the reason the sun appears to rise and set. To the ancient sky watchers, it must have seemed that the heavens turned around the earth. But it was Earth all along that turned beneath the heavens, spinning like a slow, graceful top. Yet even that motion, the one that defines our days, is just the beginning. The Earth is also orbiting the sun, looping once each year along a path more than 900 million kilometres long. Our planet travels at about 107,000 kilometres per hour on that journey. If you were to freeze time and mark Earth's position, then look again an hour later, we'd have moved more than 100,000 kilometres through space. We often talk about the passing of seasons as if they're gentle changes in weather, but really they're milestones along a colossal orbit. Each spring, summer, autumn and winter marks a new segment of that endless journey around our star. So right now, as you listen to this, you're being carried not just by a spinning world, but by a world orbiting a blazing sun, hurtling through a galactic landscape at over 100 times the speed of a bullet. Still, you don't feel a thing. The atmosphere turns with us. The oceans follow. There is no lurch, no shake, no sudden acceleration. The reason is simple but astonishing. Motion in space is relative. Unless something changes speed or direction sharply, motion feels like rest. In the vacuum of space, there is no friction to slow us down. The planet doesn't need to push against anything to keep moving. It simply coasts, steady and smooth, like a perfectly balanced wheel rolling forever. But even the Earth's orbit isn't the whole story. The sun itself, The anchor of our solar system isn't fixed. It moves too, tracing its own vast orbit around the centre of the Milky Way galaxy. It carries every planet, moon, asteroid and comet with it, all bound by gravity into a travelling family. Our Sun completes one revolution around the galaxy roughly every 230 million years. That means the last time the Sun was in this same position, dinosaurs were just beginning to appear on Earth. Imagine that for a moment. Every sunrise you've ever seen, every ancient civilization that ever gazed at the sky, every creature that ever walked or swam or flew, all of them have ridden this same spiral path around the galaxy. The entire history of life has unfolded on a planet that's never once stopped moving. And the Milky Way itself, our cosmic home, is not still either. It spins and drifts through space, pulled by the gravity of nearby galaxies and the unseen web of dark matter that threads the universe. Our whole galaxy is moving toward another, the Great Andromeda Galaxy, at a speed of about 400,000 kilometers per hour. Billions of years from now they'll merge in a slow, silent dance of stars. Even that immense collision won't feel like a crash. Space is too vast and the stars too far apart. Most will pass right by each other, unscathed, their motion simply folding into a new shape of the heavens. So when you stand under the stars and feel still, you are in fact part of an intricate cosmic ballet. Earth spins. It orbits the sun. The sun orbits the galaxy. The galaxy moves through the universe. You're in motion upon motion upon motion, a nested series of journeys so smooth you could sleep through them, which, fittingly, you might be about to do. It's strange to think that we measure our lives in moments while our planet drifts through eons. The daily turning that gives you sunrise and sunset is just a ripple on the grand ocean of motion that carries us all. We live inside a quiet storm of gravity, light and space, and yet the human body, so sensitive to the smallest tremor, detects nothing. Perhaps that's why the universe feels calm when we look at it. We are part of its stillness because we're part of its flow. When scientists first began to understand Earth's motion, it changed everything. For centuries, people believed that the stars revolved around us. The heavens were thought to turn while we stayed still. It was comforting, simple, almost poetic. Then came the realization that we were the ones moving, and the universe became a far bigger, stranger place. The Polish astronomer Nicholas Copernicus, in the 1500s, proposed that the Earth wasn't the centre, but a moving world orbiting the Sun. It was a shocking idea, not because it made the math harder, but because it shifted our sense of place. Suddenly, we were not the still point of creation. We were travellers. Galileo later strengthened that view with telescopes that showed moons orbiting Jupiter, proving that not everything circled Earth. He watched sunspots drift across the Sun's surface, evidence that even the Sun rotated. The sky, once imagined as a fixed sphere, was alive with motion. Newton added the final touch by showing that the same gravity that made an apple fall also kept the moon in orbit. Motion, he revealed, was the natural state of things. Stillness, in the cosmic sense, was the illusion. That illusion persists because our senses evolved on this moving Earth. The inner ear feels acceleration, not constant velocity. Once motion steadies, it disappears from our awareness. The same principle lets astronauts glide effortlessly in orbit, feeling no movement even as they circle the planet every 90 minutes. You're experiencing a version of that right now. Every moment your body is being carried by the rotation of the Earth, by its orbit around the Sun, by the Sun's orbit around the galaxy, and yet you feel still. You're in free fall around the Sun, balance between motion and gravity, endlessly circling but never colliding. If we could somehow step outside this system, if you could watch from a point far beyond the galaxy, you'd see Earth's path as a kind of spiral, not a flat ring around the Sun, but a twisting, forward-moving helix. The Sun races ahead, and the planets follow, looping behind it like ribbons in a wind. The orbits are never closed circles. They're graceful corkscrews winding through the galaxy. Each year, Earth completes one turn of that spiral, but the whole structure keeps drifting forward. The solar system itself moves at about 230 kilometers per second relative to the galaxy's center. In the time it takes you to blink, we've traveled dozens of kilometers farther along our path. It's humbling to realize that the stars we see at night are not permanent either. They too are in motion, each following its own orbit around the galactic core. Over thousands of years, constellations change shape. The familiar patterns of Orion and the Big Dipper slowly drift apart, the way currents rearrange leaves on a pond. To the human eye they seem eternal, but on cosmic timescales they're as transient as clouds. When astronomers map these motions, they use a kind of cosmic reference frame. Not an absolute one, because there is none, but a shared point of comparison. They measure how we move relative to the cosmic microwave background, the faint afterglow of the Big Bang. Against that ancient light, our galaxy is speeding through space at more than 600 kilometers per second. Even the universe's oldest radiation sees us as travelers. All of this motion has structure. Gravity binds it together, balancing motion with attraction, velocity with pull. The Earth moves fast enough to avoid falling into the Sun, but not so fast that it escapes. The Sun moves fast enough to orbit the galaxy, but not so fast that it flies away. Every path, every orbit, is a harmony between momentum and gravity. If Earth suddenly stopped moving, it would plunge straight into the Sun. If the Sun stopped, it would fall toward the galactic center. Motion isn't just happening, it's necessary. It's what keeps everything in balance. And yet, when we talk about the universe's movement, we often forget that motion is relative. There's no fixed point, no cosmic flaw. Everything moves relative to something else. That means you can choose any reference you like. From your perspective, the stars spin around you each night. From the Sun's perspective, Earth is the one doing the spinning. From the galaxy's viewpoint, both are spiraling together through a larger dance. There is no single truth of motion, only the relationships between moving things. That idea might sound abstract, but it's actually what makes motion feel so gentle. Because there's no edge to push against, no absolute speed. Movement through space is smooth. It's not like a car ride with bumps and turns. It's more like floating in an endless ocean where everything drifts together. You, your chair, the air in the room, the planet itself, all part of the same current. This constant drift has subtle effects. The stars we see rising and setting mark not just the rotation of Earth, but its orbit through the galaxy. Over millennia, our orientation changes, a slow wobble called precession caused by the gravitational tug of the Sun and Moon. It's why the North Star hasn't always been, and won't always be, the North Star. Our planet's axis traces a circle in the sky every 26,000 years. Even the direction we face in the galaxy changes slowly with time. The movement also carries our solar system through different regions of interstellar space. The Sun currently travels through a patch called the local interstellar cloud, itself part of a larger cavity known as the local bubble, a kind of low-density region carved out long ago by supernova explosions. Millions of years from now, we'll drift into another region, with slightly different magnetic fields and gas densities, though the change will be so gradual we'll never notice. When you take all of these motions together, the rotation of the Earth, its orbit around the Sun, the Sun's orbit around the Milky Way's drift through the universe, the total speed is enormous. Add them as vectors, and you get something on the order of hundreds of kilometers per second relative to the cosmic background. It means that as you listen to this sentence, you're moving many thousands of kilometers through space. Every breath you take happens in a new location in the universe, and yet the room feels perfectly still. Your cup sits on the table. The world doesn't shake. The stars outside your window, if you can see them, seem frozen in place. This contradiction between motion and stillness is one of the quiet wonders of physics. It reminds us that calm doesn't mean static. You can be moving through vastness and still feel peace. It's also a reminder of perspective. From a cosmic point of view, motion defines us. From a human point of view, stillness defines rest. both are true. When you lie down at night, you are in motion and at rest at the same time, depending on where you choose to stand in your mind. The universe allows both. Some people find that thought unsettling, the idea that we're never still, that we're always drifting through the void. But there's another way to see it. Motion means continuity. It means the story never ends. The Earth doesn't stay fixed. It travels through light and darkness, through seasons and ages, carrying every life and every memory along. You are part of that journey, part of a lineage of motion stretching back to the very beginning. If you could trace the atoms in your body, you'd find they were once part of ancient stars. Those stars moved through our galaxy long before the sun existed, scattering their elements in supernova, seeding the clouds that would later form our solar system. The motion of those stars, billions of years ago, helped shape the matter that would become you. In a way, you are made of motion. The iron in your blood, the calcium in your bones, the carbon in your cells, all forged and flung by movement. So when we talk about how Earth moves through the galaxy, we're not describing something separate from ourselves. We're describing home. We are passengers on a moving world, yes, but we're also the world itself in motion, the living surface of a planet spinning, orbiting, and travelling through time and space. Right now, somewhere beyond the horizon, dawn is forming. Somewhere else, night has just fallen. The Earth keeps turning, always halfway between day and night, always moving into the future. And above it all, the stars glide slowly as we orbit the galactic centre, a silent procession that has never paused. If you step outside tomorrow and look at the sky, remember that you're not looking up from a fixed spot. You're looking out from a world that's sailing through the Milky Way. You're standing on a deck of a cosmic ship that never drops anchor. Every moment you live, every thought you have, happens aboard a moving planet inside a moving solar system inside a moving galaxy. It's all one great drift, steady, silent, endless. The strange thing about motion is that we almost never feel it. You can be spinning at over 1,000 kilometers an hour, orbiting the sun at more than 100,000, and moving through the galaxy at a speed beyond imagination, and still feel nothing. The room is calm, the air still, the world quiet. It's one of nature's great illusions, the illusion of stillness. You could sit by a window and watch a tree, or a sleeping pet, or a line of distant clouds, and every sense in your body would agree that you're at rest. The ground doesn't seem to slide beneath you. The stars above don't blur into streaks. Even the atmosphere around you feels fixed in place. Yet everything from the molecules in the air to the entire planet under your feet is caught in motion so vast and continuous that your body has stopped noticing it altogether. This sense of stillness is deeply ingrained in us. For most of human history, it made perfect sense to believe that the Earth didn't move. Our ancestors had no reason to doubt their senses. The sun rose in the east, set in the west, and returned the next day in a dependable rhythm. The stars wheeled overhead in patient circles. Nothing in daily life hinted that it might be the ground, not the heavens, that was turning. The human brain evolved to trust stability. It tells us that solid things stay still unless something pushes them, and yet, in reality, every object we see is already moving in countless ways. When you look at a mountain, its vastness gives a sense of permanence. It seems like the definition of stillness. But mountains rise and erode. Tectonic plates shift beneath them at the pace of a fingernail's growth. Even at rest, their atoms vibrate with heat. The electrons inside those atoms never stop moving. So at every level, from the subatomic to the cosmic, motion never ceases. Stillness is a human perception, not a physical fact. If you've ever been on an airplane cruising steadily at altitude, you've felt a miniature version of this illusion. When the engines are quiet and the flight is smooth, you could close your eyes and believe you were sitting in a room. Without a window to reveal the clouds sliding by, motion disappears from awareness. Only when the plane turns or accelerates does your body register that you're moving at all. The same principle holds true for Earth. The planet's rotation and orbit are smooth and constant. There's no bump, no lurch, no sudden change. Because we move in perfect sync with everything around us, we feel as if we're not moving at all. This is a trick of physics and biology working together. Our bodies are built to sense acceleration, changes in speed or direction, not steady velocity. Inside your inner ear are tiny organs called the semicircular canals and the otoliths, which act as motion detectors. They're filled with fluid that shifts when you start or stop moving, sending signals to your brain about balance and orientation. But once motion becomes constant, the fluid stabilizes. The signals stop. To the brain, no change means no movement. So even though the Earth is constantly rotating, orbiting, and travelling through space, the absence of acceleration means you perceive perfect calm. This same sense tricked early observers for millennia. The philosopher Aristotle believed that the Earth was stationary because he reasoned that if it moved, we'd feel strong winds constantly blowing in one direction. When a stone was dropped, he thought, it would fall behind a moving Earth instead of straight down. These ideas matched everyday experience. No one felt the ground moving. Stones dropped at their feet. The air didn't rush away. It seemed obvious that the Earth stood still and everything else moved around it. It wasn't until careful measurements, mathematics, and telescopes entered the story that the illusion began to unravel. Copernicus proposed that the Sun, not the Earth, was at the centre of motion, but even he struggled to explain why we couldn't feel the movement. Later, Galileo showed that motion at constant speed is indistinguishable from rest. If you're inside a ship moving steadily across calm water, you can't tell whether it's moving or anchored without looking outside. The same holds true for our planet. The lack of sensation isn't a contradiction. It's exactly what physics predicts. There's another reason the illusion of stillness feels so complete. The scale of our motion dwarfs human experience. We evolved to navigate distances measured in steps, meters, and kilometers. The movements of planets and stars happen on scales so vast that even enormous speeds seem invisible. The Earth's rotation might carry you over 1,000 kilometers in an hour, but compared to the size of the planet, that motion is subtle. From your perspective, the landscape beneath you barely changes. We live inside a frame of reference that hides the grand motions from view. When you look at the night sky, the stars appear fixed, but that too is an illusion. Each one is moving, orbiting the centre of the Milky Way at hundreds of kilometres per second. They only seem still because they're so far away. Over human lifetimes, their motion is imperceptible. Only through long-term observations spanning centuries can astronomers detect their drift. To the naked eye, the heavens are a painting. To physics, they are a dance. And yet this illusion is comforting. It gives us a sense of home, a sense of orientation in a universe that otherwise moves endlessly. The Earth feels solid, dependable, safe beneath our feet, precisely because our bodies and senses are tuned to its steadiness. If we could suddenly feel the planet's rotation, it would be overwhelming, a constant rush, a never-ending pull. Stillness allows life to thrive, not because the world is still, but because it moves in a way that makes stillness possible. The same illusion plays out on smaller scales every day. When you walk through a room, you think you're moving and the room is not. But from another perspective, the room is moving too. It's rotating with the Earth, orbiting the Sun, drifting with the solar system and moving through the galaxy. You and the room share nearly identical velocities in every one of those motions, so relative to each other, you seem still. Motion is always a comparison. It only exists between things. The illusion of stillness is the absence of that difference. This idea can be demonstrated in a thought experiment. Imagine you're floating in deep space, far from any stars, any planets, anything at all. There's no window of reference, no way to tell whether you're moving or not. You could be spinning at 1,000,000 kilometers per hour, or drifting gently, or perfectly at rest, and there'd be no way to know. Without a reference, motion becomes meaningless. In that sense, stillness isn't just an illusion, it's also undefined. This perspective carries an important truth about our place in the cosmos. There is no centre of motion, no absolute frame of rest. Everything is relative. The Earth moves relative to the Sun moves relative to the galaxy moves relative to the expanding universe. Even the universe itself isn't stationary. Space itself is stretching, carrying galaxies apart. Each layer of motion makes the idea of stillness more of a human construct than a universal one, and yet, our experience of it remains deeply real. When you close your eyes and breathe, your heartbeat feels steady. You're not aware of the planet turning beneath you or the sun pulling you around its orbit. What you feel is the slow rhythm of a body that has found equilibrium in motion. Life depends on that equilibrium. Plants follow the sun's arc across the sky without sensing the spin of the world. Oceans rise and fall with tides driven by the moon's pull, a constant movement perceived as a gentle rhythm rather than chaos. The illusion of stillness isn't a failure of perception. It's the brain's way of simplifying a moving world. Sometimes this illusion breaks for a moment, and we catch a glimpse of motion. When you watch a sunset, the glowing line of the horizon seems to swallow the sun, but what you're seeing is the Earth turning away. When you feel dizzy after spinning in place, that's your inner ear protesting the sudden change in rotation. When you watch a satellite drift across the night sky, you're reminded that objects above us move independently, each with its own path. These moments are small hints that the world isn't as stationary as it feels. It's fascinating that our entire sense of time depends on motion, even though we feel none of it directly. A day is one rotation. A year is one orbit. Our calendars, clocks and routines are built on cycles of movement that we cannot feel but only observe. Without that motion, there would be no sunrise or sunset, no seasons, no rhythm to life as we know it. Stillness would mean darkness on one side of the planet forever and endless light on the other. The illusion of stillness, then, hides a truth. Motion is what allows balance. When scientists measure the Earth's movement, they do it indirectly through its effects. The Foucault pendulum, a device invented in the 19th century, shows the Earth's rotation as a slow change in the plane of the pendulum's swing. Over hours, the pendulum appears to rotate, but it's the floor beneath it, the planet itself, that's turning. This simple instrument gives visible proof of motion hidden in stillness. The same principle applies to the stars. By tracking their positions night after night, astronomers can detect the slow wobble of Earth's axis and the subtle drift of our planet through space. What feels immovable can always be shown to move, given enough patience. The illusion extends even deeper into the way we think about identity. People often talk about finding balance, about being grounded, as though stability was something fixed. But in truth, every sense of balance relies on motion. Your body maintains upright posture through constant micro-adjustments, tiny shifts of muscle and bone that keep you from toppling. Even standing still is an act of continuous movement. The same holds true for the planet and everything on it. Stability isn't the absence of motion. It's motion in harmony. It's remarkable that this harmony emerged at all. The solar system could have formed in chaos, with planets flinging off into space or colliding in violent spirals. Instead, gravity and momentum found equilibrium. The result is a system that moves constantly yet feels peaceful. Earth's orbit is stable enough to make stillness possible. You can sleep at night without fear that the world will veer off course. The sky you see tonight, though filled with moving stars, will look much the same tomorrow. If we were somehow aware of every layer of motion, the spin, the orbit, the drift through the galaxy, our daily lives would be unrecognizable. The simplest act, like setting a cup on a table, would seem miraculous. The cup doesn't slide away despite the planet spinning faster than sound beneath it. That's because motion is shared. The atmosphere, the oceans, the land, the cup, and you all move together. Relative to one another, you are still. The illusion of stillness, then, is really the experience of shared motion. That shared motion connects everything. From the smallest grain of sand to the largest galaxy, every object participates in the same fundamental laws. Gravity, inertia, and rotation tie the cosmos together in one continuous network. Your stillness and the motion of a distant star are linked by the same physics. When you realize that, the illusion becomes a comfort rather than a deception. It means you belong to the movement of the universe. Think of a night spent camping far from city lights. The stars wheel overhead. The air cools as the planet turns. Hours pass, but the ground beneath your sleeping bag feels still. In reality, you're moving through space in a slow spiral, the entire planet rotating toward dawn. The stars above you, meanwhile, are gliding through the galaxy, some toward us, some away. Every point of light is part of an immense circulation, yet the scene feels peaceful, because all those motions combine into stability. The illusion of stillness is the blending of countless movements into balance. This balance is delicate. Small changes can break it. The Earth wobbles slightly on its axis, a motion called nutation, caused by gravitational influences of the Moon and Sun. Over long timescales, these wobbles shift the climate. Ice ages come and go. Continents drift. Oceans reshape. Life adapts. Even when the illusion seems perfect, motion quietly alters the world. Stillness never lasts, but it also never vanishes. It's reborn continuously as movement settles into new harmony. That may be the most profound truth hidden in the illusion. Stillness isn't the opposite of motion. It's the feeling we have when motion is perfectly balanced. The Earth spins just right to keep the day steady. It orbits the Sun at the perfect distance to keep the climate stable. The Sun moves through the galaxy in a way that preserves the solar system structure. Everything flows, but because it flows together, we experience calm. So when you sit quietly and the world feels unmoving, you're feeling the equilibrium of cosmic motion. You are, in that moment, perfectly synchronized with the spinning, orbiting, drifting machinery of the universe. You're part of its smoothness, its rhythm, its illusion of rest. If you were to stand outside on a clear night and look toward the horizon, the world around you would seem perfectly still. The trees would sway in the wind, the stars would remain steady in their places, and nothing about the ground beneath you would suggest that you're moving at all. Yet that calm, solid surface is turning constantly. The Earth spins beneath everything we know. It has done so since before there was an ocean, before there were continents, before there were eyes to watch the sky. Every day, every night, every second, the planet rotates, smoothly, silently, endlessly. It's difficult to picture what that means, because stillness is the only motion we ever feel. But imagine this. At the equator, the ground is moving eastward at about 1,670 kilometers per hour. That's nearly half a kilometer every second. If you stood there and the rotation suddenly stopped, you would be flung eastward faster than the speed of sound. The oceans would roar from their basins, the atmosphere would tear away in shock waves, and mountains would crumble under the sudden shift. Thankfully, it never happens. The Earth turns with a grace that's almost impossible to comprehend, a speed so constant and uniform that the world feels peaceful, even as it moves at extraordinary velocity. That rotation defines almost everything we experience about the passage of time. Day and night are not things that happen to Earth. They are things Earth creates through its spin. When the planet turns toward the sun, we call it morning. When it turns away, we call it night. The slow, predictable turning of the planet brings light, shadow, warmth, and rest in a steady cycle that has shaped every rhythm of life. Plants open their leaves when sunlight arrives and close them when it fades. Animals move and sleep by the turning sky. Humans learned to mark this motion long before they understood what caused it, measuring days by the rising of the sun and the length of shadows cast on the ground. The spin isn't perfect. The Earth doesn't rotate exactly once every 24 hours relative to the Sun. Instead, it takes about 23 hours, 56 minutes, and 4 seconds to complete one full turn relative to the distant stars. That small difference means that from day to day, the Sun appears to rise about 4 minutes later against the backdrop of stars, a slow drift that adds up to one extra rotation each year. It's why the concept of a day is defined both by the Sun's position and by the Earth's rotation, two motions slightly out of sync but beautifully aligned over the long run. The direction of the spin matters too. The Earth turns eastward, which is why the Sun seems to rise in the east and set in the west. If the planet spun the other way, our mornings and evenings would reverse, and the stars would drift in the opposite direction across the sky. The tilt of the axis, about 23.5 degrees relative to the plane of our orbit, adds another layer to the experience. Because of that tilt, the path of the Sun changes with the seasons. In summer, it rises higher and sets later. In winter, it stays low and retreats early. That tilt, combined with the rotation, gives us the pattern of light and dark that life depends on. The motion itself is ancient. Scientists believe the Earth's rotation began with the same event that formed it. About 4.5 billion years ago, a cloud of dust and gas collapsed under gravity, spinning faster as it shrank. From that whirling cloud, the Sun ignited at the centre, and the leftover material flattened into a disk. Tiny grains of dust clumped together, forming larger and larger bodies, each one spinning as it collided and merged with others. Our planet was born from that spinning chaos, inheriting its rotation from the angular momentum of the disk. That rotation has slowed over time, but never stopped. It's the remnant of a birth that happened before the moon existed, before the oceans cooled, before there was anything like the world we know. You might wonder why the rotation has slowed, and the answer is found in the tides. The moon, though small compared to the Earth, exerts a gravitational pull that slightly stretches our planet. The oceans bulge toward the moon, creating what we call tides. But because Earth rotates faster than the moon orbits, those tidal bulges are always a little ahead of the moon's position. The moon's gravity tugs back on those bulges, creating a small but constant drag that slows the rotation of the Earth. As the planet slows, the moon gains a bit of that lost momentum and drifts gradually farther away, about 4 centimetres each year. The days grow longer by about 2 milliseconds per century. It's almost nothing, but over billions of years it adds up. In the distant past, days were only about 21 hours long. In the distant future they'll be longer still. That balance between the spin of the Earth and the pull of the moon is delicate but stable. It's one of the many feedback loops that keep the planet in order. The same gravitational interaction that slows the Earth also keeps the moon's rotation locked to its orbit, which is why we always see the same face of the moon from Earth. Both worlds are connected in a constant exchange of energy, a quiet dialogue across space that's been happening for billions of years. If you could somehow watch the Earth's rotation from space, it would be mesmerizing. From the perspective of a satellite in a high orbit, the planet's surface would slide beneath you like an endless tapestry of oceans, deserts, forests, and clouds. The atmosphere would swirl and shimmer, forming hurricanes that twist in opposite directions depending on which hemisphere they're in, clockwise in the south, counterclockwise in the north, a result of the Coriolis effect created by the rotation itself. That same effect shapes wind patterns, ocean currents, and even the flight paths of airplanes. The rotation of the Earth is more than a physical spin. It's the hidden hand that organises the weather and climate systems of the world. It's also what gives us our sense of direction. The axis of rotation points roughly toward a spot in the sky near the North Star, Polaris. It's not a perfect alignment, but close enough that for centuries travellers and navigators use that star to find north. The axis stays pointed in the same direction as the planet orbits the Sun, which is why the northern hemisphere tilts toward the Sun in June and away in December. Over tens of thousands of years, the axis itself slowly wobbles, tracing a circle in the sky in a motion called precession. This gradual shift means that in about 13,000 years, Vega, not Polaris, will be the North Star. Even the stability of our spin changes slowly over time, but so slowly that no single lifetime will ever notice. The precision of the Earth's rotation is something scientists can measure with astonishing accuracy. Using atomic clocks and radio signals bounced off distant quasars, they can track tiny variations in the planet's spin down to fractions of a millisecond. These fluctuations happen because of the constant exchange of energy between the atmosphere, oceans, and solid Earth. Strong winds, melting ice, even earthquakes can subtly alter how fast the planet turns. When massive glaciers melt, the distribution of mass changes, slightly adjusting the spin, much like a figure skater extending or retracting their arms to slow down or speed up. Even so, the changes are minute, imperceptible to human senses, and the overall rhythm remains steady. That steadiness is one of the reasons life could evolve and thrive here. The regular cycle of day and night regulates temperature, light, and biological rhythms. Many organisms, including humans, rely on internal clocks called circadian rhythms, which sync to the 24-hour day. The rotation provides that signal. It tells plants when to photosynthesize, animals when to hunt or rest, and people when to sleep. Without it, the balance of ecosystems would collapse. The spin of the planet isn't just a background detail of physics, it's a foundation of biology. It's interesting to think that this motion, so essential to our existence, is something we almost never think about. The ground feels fixed, but it's moving faster than any storm. The stars seem still, but their apparent motion from dusk to dawn is a direct result of the Earth's rotation. We often describe time passing as the sun rising and setting, but it's really the Earth turning and turning again. The rhythm of our days is the rhythm of rotation. Sometimes the illusion breaks just slightly, and we can sense the spin indirectly. At the equator, the centrifugal force of rotation slightly counteracts gravity, making you weigh a tiny bit less than you would at the poles. The difference is small, less than 1%, but measurable. The same force makes the planet bulge at the equator and flatten at the poles, giving the Earth an oblate shape rather than a perfect sphere. The difference in radius is about 21 kilometres, enough that satellites must account for it in their orbits. Even something as simple as a pendulum can reveal the rotation. The Foucault pendulum, swinging freely, slowly changes direction relative to the floor beneath it. Not because the pendulum turns, but because the Earth does. Watching it over the course of a day, you can see the invisible motion of the world made visible. The fact that the Earth spins so smoothly and consistently also affects the flow of time itself. Our definitions of seconds, minutes, and hours are derived from this motion, though modern science now uses atomic time for precision. Occasionally, when the planet's rotation drifts slightly due to natural fluctuations, we add or remove what's called a leap second to keep atomic clocks aligned with astronomical time. That adjustment reminds us that even something as seemingly steady as the Earth's spin is alive with subtle variation. The story of the spinning world isn't only about physics, it's also about perception. The feeling of stillness we live with each day is the brain's way of normalizing motion. You don't feel dizzy because the rotation is constant and smooth. The sky above, though it appears to move, is your reference frame turning beneath it. Every sunrise is proof of motion, every shadow that shifts through the day a quiet demonstration that the Earth is in constant rotation. From space, astronauts see this more clearly than anyone. On the International Space Station, circling Earth every 90 minutes, they watch 16 sunrises and sunsets in a single day. To them, the planet spins beneath in a blur of blue and white, continents sliding silently past. From their window, you can see the thin blue line of the atmosphere, the glowing rim of the horizon, and the slow rotation of clouds and storms. They describe it not as dizzying, but as graceful. a motion so vast and smooth that it feels like the planet itself is alive. It's humbling to realise how fragile that motion is. The Earth's rotation could, in theory, be altered by massive impacts or internal shifts. When large earthquakes occur, they can slightly adjust the planet's rotation speed by redistributing mass. After the 2011 earthquake in Japan, for example, the day shortened by about 1.8 microseconds. These are tiny effects, but they reveal how interconnected everything is, how even the deep structure of the planet and the flow of its molten core can influence the turning of the world above. The spin also generates one of Earth's most protective features, its magnetic field. The movement of molten iron in the outer core, combined with rotation, creates a dynamo effect that produces the magnetic field surrounding the planet. This invisible shield deflects charged particles from the sun and cosmic rays from deep space, protecting the atmosphere and life itself. Without the rotation, the dynamo would weaken, the field could collapse, and the solar wind would strip away the air as it has on Mars. Our spinning world doesn't just give us day and night, it gives us safety. When you consider how many processes depend on this single motion, it becomes difficult to separate what we call normal life from the turning of the Earth. The timing of seasons, the direction of winds, the flow of ocean currents, the magnetism that guides compasses and migratory animals, the cycle of sleep and wakefulness, all of it arises from the spin. The simple act of rotation sustains the complexity of everything else. And still, as you sit here listening, you feel none of it. You can close your eyes and breathe, and the planet will continue its turn beneath you without pause. You're carried along with it so perfectly that the motion disappears into stillness. The stars outside your window will shift slowly westward through the night. The moon will glide across the sky. The planet will complete another fraction of its endless spin, and you, without moving a muscle, will have travelled thousands of kilometres through space. The next time you watch the sun sink below the horizon, you might imagine, just for a moment, that you're not watching it move away. You're watching yourself turn. The edge of the world is rising to meet the night, carrying you gently into darkness. The stars that appear are not rising, but being revealed as the planet continues its rotation. It's a quiet, precise, tireless motion, a clock that's been ticking for billions of years. The spin of our planet gives us day and night, the steady rhythm that shapes the hours of every living thing. But there's another slower motion unfolding at the same time, a journey so vast that no one can ever feel it, yet every sunrise and every season is part of it. The Earth doesn't only turn on its axis, it also travels around the sun, following a wide, looping path that defines the length of a year. This path isn't a perfect circle, but close enough that for most of history it seemed like one. It's the great orbit that carries us endlessly through the light and shadow of the solar system. If you could step back far enough, away from the Earth, away from the planets, and look down from above the sun's north pole, you'd see the whole solar system arranged like a great wheel. The planets would appear as tiny beads of light tracing their orbits around the centre, each moving at its own pace. Mercury would zip around in just 88 days, Venus in 225, and Earth would glide along its path once every 365 1/4 days. Mars, slower still, would take nearly 2 Earth years to complete its turn. The farther a planet is from the Sun, the longer and slower its orbit becomes, each one moving to the same law of motion that keeps the system balanced. The shape of Earth's path is what astronomers call an ellipse, a gentle oval, not a perfect circle. The Sun sits slightly off-centre within it. This means that over the course of a year our distance from the Sun changes. In early January we are closest, at a point called perihelion, about 147 million kilometres away. In early July we're farthest, at aphelion, about 152 million kilometres away. The difference, though enormous in scale, is small enough that it doesn't cause the seasons. Many people imagine that summer happens when we're close to the sun, but it's actually the tilt of the Earth's axis that brings warmth and light to one hemisphere and darkness to the other. The distance change only makes a small difference in the intensity of sunlight, but it's enough that our planet's orbit breathes slightly, a slow in and out motion as we circle our star. The speed of this motion is extraordinary. The Earth travels at roughly 107,000 kilometers per hour along its orbit. In a single second, it moves about 30 kilometers through space. Every minute, nearly 2,000 kilometers. By the time you finish this sentence, you'll be thousands of kilometers farther along the planet's path around the Sun, though you won't have felt a thing. The orbit is smooth and steady, a balance between two forces that never stop acting on each other: gravity and motion. Gravity, the pull of the Sun's immense mass, tries to draw the Earth inward. Motion, the momentum of our planet as it moves through space, tries to send it flying outward. The result is neither falling in nor escaping, but a continuous free fall that loops forever. The Earth is always falling toward the Sun, but never reaching it, because its sideways motion keeps it perpetually missing. That's what an orbit really is, an infinite fall that never ends. This balance was first described by Johannes Kepler in the early 1600s. He found that planets move in ellipses and that their speeds change slightly as they move closer to or farther from the Sun. When the Earth is near perihelion, it moves faster. When it's near aphelion, it slows down. The total energy stays the same, but the exchange between kinetic and potential energy creates a graceful variation, like the steady breathing of a cosmic lung. Later, Isaac Newton showed why this happens. His law of universal gravitation explained that every mass attracts every other mass, and the motion of the planets is the natural consequence of that pull. The same force that keeps an apple on the ground keeps the Earth in orbit. The same mathematics describe both. It's a humbling thought that the vast architecture of the solar system is governed by the same rules that shape the fall of a pebble or the swing of a pendulum. The Earth's orbit may be grand, but it isn't special. It's part of the universal order that extends from the smallest dust grain to the largest galaxy. The orbit also defines the rhythm of the seasons, though not because of distance. The Earth's axis remains tilted at about 23.5 degrees relative to its orbital plane. That means that as the planet moves around the Sun, each hemisphere alternately leans toward or away from the light. When the northern hemisphere tilts toward the Sun, it experiences summer, longer days, higher sun angles, and more direct light. At the same time, the southern hemisphere tilts away and experiences winter. Half a year later, the situation reverses. Spring and autumn come when the tilt neither favours nor opposes the Sun, and day and night are nearly equal across the world. This simple tilt, combined with the orbital motion, gives rise to almost everything we associate with time and change. The migration of animals, the growth of plants, the weather patterns that feed rivers and shape climates, all of them trace their origins to the great circle we travel each year. Every habit of life is synchronized to this motion, even if we rarely think of it. It's easy to take for granted that our orbit is stable, but in the long history of the solar system, stability is something that had to be earned. When the planets first formed, their paths were chaotic. They collided, scattered, and shifted as gravity reshaped the early solar disk. Over millions of years, the orbit settled into the pattern we see now, nearly circular and gently spaced. The Earth's current orbit is remarkably stable compared to many other worlds. Its slight eccentricity, the measure of how elliptical it is, helps keep the climate relatively consistent over geological timescales. A more elongated orbit would bring dramatic changes in temperature and habitability. The fact that our orbit is nearly circular is one of the quiet reasons life could flourish here. The path itself isn't marked by any trail or track. The Earth leaves no wake as it moves through the vacuum of space. If you could trace the orbit visually, it would look like an invisible loop around the Sun, defined only by motion and gravity. But in reality, the Earth never returns to exactly the same place. The Sun itself is moving, orbiting the centre of the Milky Way, and dragging the entire solar system with it. So as the Earth follows its path, it's also being carried forward through the galaxy. The result is a spiral, not a flat circle. A continuous helix winding through space. Each year, the planet completes another loop, but that loop has moved tens of billions of kilometres farther along the galactic path. Our orbit is a circle only in relative terms. In the broader view, it's a journey without repetition. When we describe the orbit as a year, we're naming something that has existed since before there were calendars, before there were people, before there was even solid ground to stand on. The length of a year is built into the structure of the solar system itself. It's the time it takes for our planet to make one revolution around its star, about 365.225 days. The extra quarter day adds up, which is why every 4 years we insert a leap day to keep our calendars aligned. Without that adjustment, the seasons would slowly drift over centuries, and eventually summer would fall in December and winter in June. The leap year is our small human correction to the clockwork of celestial motion. Even the speed of our orbit isn't perfectly constant. Tiny influences from the Moon, other planets, and even the non-uniform distribution of mass within the Earth create small variations. Jupiter, with its immense gravity, tugs subtly on the Earth as it moves, causing minute shifts that astronomers can detect with precise instruments. These gravitational interactions are part of what keeps the solar system stable over billions of years, as the planets gently adjust to each other's pull in a cosmic balancing act. The Earth's orbital plane is tilted slightly relative to the Sun's equator by about 7 degrees. This tilt, along with the inclinations of the other planets, gives the solar system a slight three-dimensional texture. The orbits are not perfectly flat, but slightly offset, like a series of thin, overlapping rings. From the outside, it would look almost flat, but not entirely. The Earth's orbit wobbles slightly over time due to gravitational influences, creating long-term cycles known as Milankovitch cycles, which affect climate patterns on scales of tens to hundreds of thousands of years. These slow shifts have contributed to the waxing and waning of ice ages, showing again that even the smoothest motion has layers of complexity. The path we travel is illuminated by sunlight, but space itself is mostly empty. Between the planets lies an expanse of dust, gas, and occasional wandering asteroids, the remnants of the solar system's formation. Occasionally, comets dive inward from the distant edges of the Sun's domain, tracing long glowing arcs as they fall and then retreat. The Earth sometimes passes through their debris trails, creating meteor showers that streak across the night sky. These events are gentle reminders that our orbit crosses paths with countless others, each one leaving its faint signature in the shared space around the Sun. What's remarkable about this great orbit is how precisely it can be measured. Modern astronomy can track the Earth's position to within centimetres, thanks to laser-ranging experiments that bounce signals off reflectors left on the Moon by the Apollo missions. The timing of radio pulses from distant pulsars, the behaviour of spacecraft and the alignment of celestial events all confirm the extraordinary accuracy of our knowledge. The orbit may be invisible, but it is not uncertain. Every second, scientists can tell you almost exactly where the Earth is in its endless path. This precision allows us to predict eclipses, transits and alignments far into the future. It's how we send spacecraft to other planets, timing their launches so they intercept their targets along their orbits. Every interplanetary mission is a direct application of the same principles that keep Earth moving. The balance of gravity and momentum. The laws of motion that describe our orbit also describe the flight of every probe and rover exploring the solar system. Despite all that motion, the sense of stillness remains. You can go outside on a quiet morning, feel the ground firm beneath your feet, and the sun's warmth on your face. Nothing about that experience suggests that you're hurtling through space at tens of kilometres per second. The orbit is too large, too smooth, to leave any trace of motion in your senses. What you feel is equilibrium, the same delicate balance that defines all motion in the universe. If the Earth's orbital speed were slower, we would fall closer to the Sun. If it were faster, we would drift farther away. The exact speed we have is what keeps us in a stable, life-supporting zone. This region, sometimes called the habitable zone, is where temperatures allow liquid water to exist on a planet's surface. It's a narrow range, neither too hot nor too cold, and the Earth's orbit sits comfortably within it. Small changes could make enormous differences. A shift of even a few percent in our distance from the Sun would alter the climate dramatically. Yet for billions of years, the orbit has held steady enough to allow life to evolve and persist. The tilt of the axis and the orbit together give rise to a complex dance of light that unfolds over the course of each year. The Sun's position in the sky changes not only in height, but also in the length of its path from sunrise to sunset. Near the equator, the change is small. Near the poles, it's immense. In the far north and south, there are times when the Sun never sets, and others when it never rises. These extremes are expressions of geometry, the tilt and orbit working together to paint the shifting boundaries of day and night across the planet's surface. When you consider the scale of this motion, it's easy to forget that the Earth's orbit is only a small part of a much larger story. The Sun itself is moving around the centre of the Milky Way at about 230 kilometres per second, taking the planets with it. That means our orbit is carried forward in a giant spiral, each loop a new step along the galaxy's arm. The Earth never travels the same path twice. Each year's circle is drawn in a different place in space. The journey is continuous, unending, and quietly magnificent. If you could watch this from outside the galaxy, you'd see the solar system as a cluster of tiny lights following a glowing trail. The Sun leading, the planets swirling behind like sparks in a gentle current. The Earth's orbit would look like a fine thread in that pattern, barely visible against the immensity of the Milky Way. And yet, from our point of view, it's everything. That single loop is where all of human history has unfolded. Every thought, every life, every dream has happened somewhere along that unbroken path. The awareness of this motion changes nothing about how the world feels, yet it deepens the sense of belonging to something vast. The orbit doesn't ask us to do anything, it simply carries us. It defines the rhythm of time, but it never interrupts. The seasons turn, the sun rises and sets, the Earth continues along its endless trajectory, never hurried, never delayed. And as it does, it brings along all the companions of the solar system, planets, moons, asteroids, comets, each one moving to its own beat within the shared gravitational web. Together, they create a choreography of motion around the Sun, a quiet dance that has been unfolding for billions of years and will continue long after this particular year, this particular moment, has passed into memory. The Sun, the great centre of our solar system, feels like the most stable point we know. Every morning it rises in the same direction, glowing with the same light, anchoring our sense of time and place. For most of human history, it was thought to be unmoving, a fixed point around which everything else revolved. But the truth is quieter, deeper, and far more fascinating. The Sun, like everything else in the universe, is in motion. It has been moving since before the Earth existed, tracing its own vast orbit through the Milky Way. The light that warms your skin and the gentle gravity that holds the planets in their places all belong to a star that is itself a traveller, crossing interstellar space on a journey that will last hundreds of millions of years. The Earth doesn't orbit a stationary object. It follows a star that's always on the move. The Sun is one of roughly 200 billion stars in our galaxy, each one following its own path around the galactic centre. If you could somehow step back and watch from far above the Milky Way, you'd see a vast rotating disk of light, a spiral of stars, gas and dust all turning slowly around a dense, invisible hub. Near the centre lies a supermassive black hole, about 4 million times the mass of our Sun, hidden by clouds of gas and dust, but exerting a gravitational influence over the entire galaxy. Every star, including the Sun, orbits that centre, caught in its deep gravitational well. The Milky Way is enormous. From one side to the other, it spans about 100,000 light-years. The Sun sits roughly halfway out from the centre, about 27,000 light-year away, nestled in a region between two spiral arms called the Orion Spur. Here, the Sun and its planets orbit the galactic centre at a speed of about 230 kilometres per second, fast enough to circle the galaxy once every 230 million years. That means that since the Earth formed about 4.5 billion years ago, the solar system has made nearly 20 complete orbits around the Milky Way. Every era of life, every extinction, every rise of civilization has happened during one tiny segment of that immense journey. The path the Sun follows isn't a simple circle. It moves in a slightly wavy orbit, bobbing up and down through the plane of the galaxy as it travels around. Sometimes it's a little above the galactic disk, sometimes below, moving in a kind of gentle oscillation. It also drifts slightly inward and outward, tracing a slow spiral that changes subtly with each revolution. These motions are caused by the gravitational pull of other stars, giant molecular clouds, and the uneven distribution of mass throughout the galaxy. The result is that the Sun's path is more like a long, slow ripple through a sea of stars than a perfectly flat orbit. If you could see this motion from outside, it would look serene. The Sun would glide smoothly along, dragging its retinue of planets behind it, each one looping around in a spiral pattern. Mercury closest, then Venus, Earth, Mars, and the rest, all tracing graceful helices through the interstellar dark. To the human eye, it would look almost like a glowing thread unwinding in space. Each loop of the Earth's orbit would be a small twist along that thread, never overlapping exactly, each one farther along the galactic path than the last. It's a continuous voyage, not a closed circuit. The solar system never returns to the same place twice. The region of the galaxy we pass through isn't empty. It's filled with thin clouds of gas and dust, remnants of long-dead stars and raw material for new ones. The Sun and its planets currently travel through a region known as the local interstellar cloud, a sparse, wispy patch of hydrogen and helium gas stretching about 30 light-years across. It's part of a larger structure called the local bubble, a cavity in the galactic disk created millions of years ago by a series of supernova explosions. Those ancient blasts swept away the surrounding gas, leaving behind a low-density region that the Sun happens to be passing through. Even though the interstellar medium is extremely tenuous, with fewer than 1 atom per cubic centimetre, it still interacts with the solar system in subtle ways. The solar wind, a constant stream of charged particles flowing outward from the Sun, meets the thin gas of interstellar space at a boundary called the heliopause. This is the edge of the Sun's influence, the outer boundary of the bubble carved by its wind. Beyond that point, the particles from the Sun slow down and merge with the surrounding interstellar medium. Spacecraft like Voyager 1 and Voyager 2 have crossed this boundary, becoming the first human-made objects to enter interstellar space. They still move with the Sun, but they now drift in the same vast ocean through which our star sails. As the Sun travels, it carries the entire solar system along with it. Planets, moons, comets, and asteroids all bound together by its gravity. Every particle that orbits the Sun shares this motion. The comets in the distant Oort cloud, stretching perhaps halfway to the nearest stars, form the outermost fringe of the solar system's domain, and even they move with the Sun through the galaxy. The scale is staggering. The solar system's influence extends for trillions of kilometres, yet it remains just a tiny speck compared to the distances between stars. The nearest neighbouring star, Proxima Centauri, lies about 424 light-years away, roughly 40 trillion kilometres. In its orbit, the Sun moves among other stars that are also on their own paths. Some drift alongside us for a time before slowly diverging. Others pass nearby, changing the distribution of comets in the Oort cloud. or slightly altering the sun's motion through their gravity. Every few million years, a star comes relatively close to our solar system, close in cosmic terms, though still many trillions of kilometres away. These encounters are gentle but cumulative. They subtly reshape the long-term trajectory of the Sun and the architecture of the solar system, reminders that even on this grand scale, nothing moves entirely alone. The motion of the Sun through the galaxy isn't random. It follows the collective flow of the Milky Way's disk, where most stars move in roughly the same direction around the centre. The entire disk itself rotates, though the rotation isn't uniform. Stars closer to the centre move faster than those farther out, a pattern known as differential rotation. This means that over time, the spiral arms of the galaxy don't stay fixed. They shift and reform like waves on a slow-moving sea. The Sun's journey carries it through these spiral arms periodically, passing through regions of higher density where stars are born, and then moving into calmer, emptier regions between them. Astronomers think the Sun completes one circuit around the galaxy roughly every 230 million years, but the precise duration of a galactic year can vary slightly depending on the method of measurement. To put that in perspective, one galactic year ago, during the Sun's previous full orbit, the earliest dinosaurs were walking on Earth and the first mammals were just emerging. Every revolution of the Sun around the Milky Way marks a new chapter in the planet's deep history, written not in human years but in cosmic ages. The Sun's motion isn't just lateral, it also moves vertically relative to the galactic plane, oscillating up and down roughly every 60 million years. When it passes through the plane, the density of stars and interstellar matter is slightly higher. Some researchers have speculated that these crossings could influence events on Earth, perhaps by disturbing distant comets or subtly affecting the climate over geological timescales, though such ideas remain under study. Whether or not there's a direct connection, the fact that our star bobs like this through the galaxy shows how dynamic and interconnected everything is. If we could visualize the Sun's path through the Milky Way, we'd see that it traces a vast, gently curving line around the center, looping up and down as it goes. Around it, the planets describe smaller spirals, all nested together. The entire system moves as a unit, like a family of travellers on the same road. The Sun provides light and gravity, the planets provide motion and variety. Together, they form a self-contained structure that drifts through space, changing position but not identity. Despite the Sun's immense speed, space is so empty that it rarely encounters anything directly. Even in the densest regions of the galaxy, stars are separated by light years. If the Sun were the size of a grain of sand, the nearest star would still be several kilometres away. Collisions between stars are extremely rare. The Sun's path through the galaxy is smooth, unhurried and safe, at least on timescales we can imagine. It moves through an environment vast enough to seem eternal, yet delicate enough that its gravity continues to guide everything that orbits it. The motion of the Sun has subtle consequences for what we observe in the sky. The stars we see at night aren't fixed. Their apparent positions slowly shift because of the Sun's movement. Over tens of thousands of years, constellations change shape as nearby stars drift relative to distant ones. The pole star, which currently happens to align closely with Earth's axis, won't always hold that place. As both the Earth and the Sun move, the entire celestial map gradually rearranges itself. The sky that our distant descendants see will not be the same sky we know. Even the cosmic background radiation, the faint afterglow of the Big Bang, reveals the Sun's motion. When scientists measure the temperature of that ancient light across the sky, they find a slight difference. It's a bit warmer in the direction we're moving and cooler in the opposite direction. This effect, known as the cosmic microwave background dipole, tells us that the entire solar system is moving at about 370 kilometers per second relative to the rest frame of the universe. It's the ultimate proof that motion never stops, even at the largest scales. The sun's energy, meanwhile, is what makes all this motion meaningful to us. Deep within its core, hydrogen atoms fuse into helium, releasing enormous amounts of energy. That energy travels outward, bouncing from particle to particle, slowly making its way to the surface before streaming into space as light and heat. The sunlight that reaches Earth left the sun about 8 minutes ago. During those 8 minutes, the sun itself has moved thousands of kilometres along its galactic path, carrying the beam of light slightly forward even as it spreads outward in all directions. Every ray that touches the Earth arrives with a trace of that motion embedded in it. It's worth remembering that the sun's stability is an illusion of scale. To us it seems eternal, but it is a dynamic object constantly churning, rotating, and changing. It spins once every 27 days at the equator, though the poles rotate more slowly because the sun is not solid. Magnetic fields twist and snap on its surface, producing sunspots and flares. Streams of charged particles flow outward as the solar wind filling the heliosphere. All of this activity travels with the sun as it moves through the galaxy, creating a moving bubble of energy that shelters the planets within. The sun's journey is shared by every world it holds. Mercury, scorched and airless, clings close to the light. Venus swirls with clouds thick enough to hide its surface. Earth, with its oceans and life, follows at just the right distance. Mars, colder and drier, tags along beyond us. Farther still, the gas giants orbit with their moons, some icy, some volcanic, all part of the same travelling family. Together they move as one, bound by the sun's gravity and carried through the galaxy as a single coherent system. If we could somehow pause the galaxy's rotation and watch the sun glide past, we'd see it surrounded by a faint glow, not from its own light, but from the dust and gas it disturbs as it moves. The solar wind compresses the interstellar medium ahead of it, forming a bow shock like the wave at the front of a ship. Behind it, the heliotail stretches for billions of kilometres, a faint trail of charged particles flowing in its wake. It's invisible to the eye but detectable with sensitive instruments, a subtle signature of the sun's motion through space. The sun has been making this journey for nearly 5 billion years and will continue for billions more. Over that time, it will slowly change. As it burns through its hydrogen fuel, it will brighten and expand. In about 5 billion years, it will enter its red giant phase, swelling large enough to engulf Mercury and Venus and possibly Earth. Long before that happens, the increasing brightness will alter the planet's climate, warming it beyond the point where oceans can exist. The sun's orbit around the galaxy will continue, but the solar system as we know it will transform. By then, the sun will have completed many more galactic revolutions. It will have crossed spiral arms, passed through interstellar clouds and shared space with countless new stars. Its journey is one of motion through both space and time, not just across distance, but through epochs. Each orbit around the Milky Way is a new sweep of history, carrying whatever worlds and life it sustains into the next chapter of cosmic evolution. When you look up at the sun from Earth, it's easy to think of it as the fixed centre of everything, but in truth, it's as much a traveller as any of us, a moving beacon of light, leading its small family of planets through the darkness. Every sunrise is a moment on that voyage, another turn along the galaxy's endless curve. The light that spills across the world each morning comes from a star that's never in the same place twice. And as it continues onward, it carries us with it, Earth, Moon, and all, through the wider sea of stars. The path it follows is one thread among billions, each star weaving its own trajectory, all together forming the living structure of the Milky Way. The sun's motion is just one piece of that grand, quiet movement, the background current that pulls everything along. The solar system, bound tightly to its star, drift through the galaxy, not as a single dot, but as a miniature world in motion. Planets orbiting, moons circling, comets sweeping past, all drawn forward by the same unseen hand. the Sun does not travel through the galaxy alone. Around it, bound by gravity and moving in perfect rhythm, the planets, moons, asteroids, and comets trace their own patterns through space. Each one follows a path that seems simple from a distance, but becomes endlessly intricate the closer you look. Together they form a structure both stable and dynamic, a family of worlds orbiting a common star, each influenced by the others, all sharing the same great motion as they journey around the Milky Way. The solar system is often imagined as a flat diagram, concentric rings drawn around a glowing centre, but in truth it is far more alive. Each planet moves at a different speed, along a slightly tilted plane, creating a three-dimensional choreography that never stops. From the smallest asteroid to the largest gas giant, everything that circles the Sun is part of the same gravitational conversation. Some move quickly, looping around the star in months. Others drift slowly, taking centuries to complete a single orbit. But together, they create a pattern that has remained balanced for billions of years. At the heart of this dance lies gravity. It is the force that binds everything to everything else, the silent conductor of motion. The Sun contains about 99.8% of the solar system's total mass, and its gravity shapes the orbits of all the planets. Each planet in turn exerts a smaller pull on the Sun and on the other planets. The result is a complex web of interactions that can be described with mathematics, but is easier to imagine as a graceful motion. A collection of bodies moving in harmony, their mutual pulls creating a system that remains coherent despite constant motion. The innermost world, Mercury, moves the fastest. It whirls around the Sun every 88 days, its small orbit almost circular but slightly stretched. Its surface, cratered and scorched, faces temperatures that swing from freezing to blistering in the span of a single rotation. Because it's so close to the Sun, Mercury experiences strange effects from gravity. Its orbit slowly rotates over time, a phenomenon known as precession. This subtle motion was one of the first clues that Newton's laws, though remarkably accurate, were not the whole story. Only Einstein's general theory of relativity could fully explain the precise rate of Mercury's orbital shift, showing that even in this small inner part of the solar system, space and time are slightly curved by the Sun's immense mass. Farther out lies Venus, almost the twin of Earth in size but utterly different in nature. Its thick atmosphere traps heat so efficiently that its surface stays hot enough to melt lead. Venus moves around the Sun once every 225 days, but its rotation is peculiar. It spins backward compared to most other planets, meaning the Sun rises in the west and sets in the east. It also rotates very slowly, taking 243 Earth days to complete a single turn, longer than its year. The result is a world where day and night, heat and shadow, unfold at a pace so alien that no human rhythm could follow it. Yet Venus remains locked in step with the solar system's overall pattern, circling steadily in its place, contributing to the gravitational balance that defines the whole. Then comes Earth, our moving home, orbiting at an average distance of about 150 million kilometres from the Sun. It travels at just the right speed, not too fast, not too slow, to maintain a nearly circular path. That balance, achieved through billions of years of evolution, keeps the climate within the range that allows liquid water, weather, and life. The Earth's motion is not isolated. It's constantly influenced by the Moon, by Venus, and even by the distant pull of Jupiter. Tiny changes in its orbit accumulate over long timescales, causing slow variations known as Milankovitch cycles that have shaped ice ages and climate shifts throughout history. Even something as stable as a planet's orbit carries traces of interaction with the rest of the cosmic dance. Beyond Earth lies Mars, smaller, colder, and marked by a landscape of deserts, mountains and canyons. Mars orbits the Sun once every 687 Earth days, nearly twice the length of our year. Its thin atmosphere and tilted axis give it seasons much like Earth's, though more extreme and longer lasting. Mars and Earth occasionally align on the same side of the Sun, coming close enough that spacecraft can travel between them with relative ease. The gravitational interplay between the two, though faint, subtly affects their orbits, showing that even across millions of kilometres, the planets are never truly separate. Past Mars lies the asteroid belt, a vast region filled with rocky fragments, remnants of a world that never formed. These asteroids range from tiny pebbles to dwarf planets hundreds of kilometres across. Their orbits form a kind of transitional zone between the inner, rocky planets and the outer gas giants. The belt itself is shaped by Jupiter's gravity, which prevents the material from coalescing into a single planet. Instead, the asteroids remain in a delicate balance, their paths shaped by resonances with Jupiter's motion. Some are drawn into stable patterns, others flung away. The belt is not dense as old depictions suggested. It's mostly empty space, with vast distances between each object. But in the grand choreography of the solar system, it serves as a kind of rhythm, a quiet pause before the slower, deeper motions of the outer worlds. Then, dominating the outer system comes Jupiter, the giant among planets. It contains more mass than all the other planets combined. Its gravity influences not only its own moons, but the entire architecture of the solar system. Jupiter orbits the Sun once every 12 Earth years, moving at a speed slower than Earth's but with far greater momentum. Its presence stabilizes some orbits and disrupts others. Without Jupiter, the inner planets might have faced far more frequent impacts from comets and asteroids. With it, many of those objects are either captured or flung outward into distant space. The balance of safety and danger that defines Earth's long-term habitability owes much to this giant's steady presence. Saturn follows, a world of rings and shadows. It's slightly smaller and less dense than Jupiter, but still immense. Saturn orbits the Sun once every 29 years, its path marked by the glow of its icy rings. Particles of ice and rock, each one following its own miniature orbit around the planet. The rings are a kind of echo of the solar system itself, a smaller scale version of the same pattern. Countless bodies, each moving according to gravity, yet forming a single coherent structure. Saturn's moons too participate in this harmony. Some orbit within gaps in the rings, others tug gently on them, shaping their edges and divisions. The entire system of Saturn is a microcosm of the solar system's larger dance, a perfect demonstration of motion and order coexisting in complexity. Beyond Saturn lies Uranus, the first planet discovered in modern times with the aid of a telescope. Its orbit takes 84 Earth years to complete, and its rotation is tipped dramatically. It spins almost on its side, as if it were rolling along its path. This extreme tilt gives Uranus seasons that last more than 20 Earth years each. For decades at a time, one pole faces the Sun continuously, while the other lies in deep darkness. The cause of the tilt may have been a colossal impact early in its history, yet even with this unusual orientation, Uranus moves in harmony with the rest, following the same gravitational rules that bind the entire system. Farther still, Neptune completes the visible family of planets. It orbits once every 165 Earth years, tracing the outer edge of the planetary system. Beyond it, in the dim reaches where sunlight grows weak, lies a region filled with icy worlds, the Kuiper Belt. Here are objects like Pluto, Eris, Haumea, and Makemake, small and cold, each following its own path along the frozen frontier. These dwarf planets remind us that the solar system doesn't end at Neptune but continues outward in a slow fade, where the boundary between the Sun's influence and interstellar space gradually blurs. Even beyond the Kuiper Belt lies the Oort cloud, a vast sphere of icy bodies extending perhaps halfway to the nearest stars. These distant comets orbit the Sun on paths so long that a single revolution might take millions of years. Some are disturbed by passing stars or the tidal forces of the Milky Way, sending them inward toward the planets. where they become bright comets visible from Earth. Every comet that crosses our sky is a messenger from that outer realm, a trace of the solar system's distant edge entering briefly into our neighbourhood before retreating again into the dark. All of these objects, planets, moons, asteroids, comets, move together, bound by gravity and time. Their orbits are stable enough to last for billions of years, yet flexible enough to respond to subtle changes. The solar system's stability is not static but dynamic. The planets constantly adjust to each other's presence, exchanging tiny amounts of energy through gravitational tugs. This process is called orbital resonance, and it appears throughout the system. Jupiter's moons, for example, Io, Europa and Ganymede, are locked in a precise resonance where for every orbit Ganymede completes, Europa orbits twice and Io 4 times. This regular pattern keeps their orbit stable and creates tidal forces that generate internal heat. On Io, that heat drives constant volcanic activity, making it the most volcanically active world in the solar system. On Europa, it likely maintains a subsurface ocean beneath the ice, a potential habitat for life. The same kinds of resonances shape the gaps in Saturn's rings and the distribution of asteroids in the belt. They're like the harmonics of a musical chord, simple ratios that keep complex systems in balance. The solar system's dance, though chaotic in detail, remains stable over immense spans of time because these patterns distribute energy evenly. It's a kind of natural order that emerges from the laws of physics, requiring no conductor, no intention, only gravity and motion. The Sun, massive though it is, does not remain perfectly still at the centre of this system. The combined gravitational pull of the planets, especially Jupiter and Saturn, causes it to move slightly in response. The Sun and planets all orbit a common centre of mass called the barycenter, which sometimes lies just outside the Sun's surface. This means the Sun wobbles gently as the planets move, shifting position in a slow, subtle way. Even the star itself participates in the dance, responding to the gravity of its companions. The entire solar system is thus a single interconnected structure, each part influencing every other, every motion contributing to the whole. The patterns of movement are not just mechanical, they define how the system evolves. Planetary orbits can change slightly over millions of years due to small perturbations. Occasionally these shifts align in ways that cause temporary instability. A planet's orbit might become more elongated, or an asteroid might be nudged into a new path. Over billions of years, these effects can reshape the system's layout, though the changes are slow beyond comprehension. The solar system as we know it is both ancient and still in motion, not frozen, but evolving in slow motion. If you could observe the solar system from far away, you would see the planets tracing glowing trails around the Sun, the inner ones spinning quickly and the outer ones drifting slowly, their paths twisting together like threads of light. The entire structure would be moving through the galaxy as one, the Sun leading, the planets swirling behind. It would be a sight both simple and intricate, an immense mechanism powered by gravity, yet delicate enough that even small forces can create new patterns over time. The idea of stability in this system is relative. Astronomers simulate the motions of planets for billions of years and find that while the overall structure remains intact, the details constantly shift. Orbits change phase, inclinations vary, and resonances appear and fade. The system is stable not because it's unchanging, but because its changes are balanced. Motion itself creates order. Every fluctuation finds equilibrium again. That balance is what allows the solar system to persist, not in stillness, but in continual motion. This dance also connects to the origins of everything we see. The same rotation that keeps planets in orbit once shaped their formation. When the Sun was young, it was surrounded by a disk of gas and dust rotating around it. Over time, that material clumped into larger and larger bodies, colliding, merging, and settling into the orbital plane. The leftover debris became the asteroids, comets, and small worlds that still populate the system. What we see now is the long-term outcome of that original disk, motion that began billions of years ago and never stopped. Even now, new motions continue to emerge. The solar system is filled with smaller objects whose orbits cross and interact. Near-Earth asteroids, distant trans-Neptunian objects, and interstellar visitors like Oumuamua and Borisov, which pass through from other star systems. Each one follows the same laws, entering and leaving the solar system according to the same gravitational rules. They remind us that this dance is not isolated, but part of the greater movement of the galaxy, where stars and their planets exchange material over time, connected by the shared flow of gravity. The balance of motion also influences light and perspective. From Earth, the movement of the planets against the background of stars creates patterns we call conjunctions and oppositions, alignments that ancient observers once interpreted as omens or messages. Today, we understand them as the geometry of orbits, the way different worlds line up along the same plane as they circle the Sun. When Venus or Mercury passes directly between the Earth and the Sun, we see a transit, a tiny shadow crossing the solar disk. These events are rare, predictable outcomes of the same orbital mechanics that have been unfolding since the solar system began. In every sense, the solar system is not a static arrangement of objects, but an ongoing process. Each orbit is a continuation of motion inherited from the birth of the Sun itself. Every planet's path is both unique and part of a collective rhythm. The gravitational links between them extend across space, creating invisible lines of force that connect every world to every other. The whole system breathes and turns like a living structure, one where balance arises naturally from the pull and release of gravity. From our small vantage point on Earth, this might seem abstract, but it's the foundation of everything we know. The predictability of sunrise, the stability of seasons, the long-term safety of our orbit. All of it depends on this great dance continuing smoothly. We are passengers in the middle of it, moving along with the rest, unaware of the complexity beneath the calm sky. The harmony we experience is not the absence of motion, but the result of countless motions working together. Every orbit, every spin, every subtle drift of the solar system unfolds within something greater still. Beyond the Sun's gravity, beyond the farthest edge of the Oort cloud, lies the galaxy that holds it all, the Milky Way. To the Kahir from Earth on a clear night, it appears as a pale band of light stretched across the sky, faint and misty, like a distant cloud. But that soft glow is not a cloud at all. It's the combined light of hundreds of billions of stars woven together into a single, enormous structure, one that is itself in constant motion. The Milky Way may look serene, but it is not still. It is a rotating system, a vast spiral of stars, gas, dust and dark matter, all bound by gravity and turning slowly around its centre. Every star you can see, and countless more that you can't, are part of this motion. The Earth orbits the Sun orbits the galaxy, and the galaxy itself moves through space, following its own trajectory among other galaxies. There is no edge to the motion. Each layer carries the next, and the Milky Way is one of those layers, immense, ancient, and never at rest. If you could see the Milky Way from far above, from some imaginary vantage point outside its disk, you'd see a spiral with long, graceful arms curling outward from a bright core. The arms are not solid structures, but patterns, regions where gas and stars are more densely packed, moving in waves that travel through the galactic disk. The stars themselves move in and out of these arms, like cars in slow-moving traffic, gathering briefly and then drifting apart again. The spiral arms are places of birth, where clouds of gas collapse under gravity to form new stars. Over time, the young stars drift away, and new ones take their place. The pattern persists, even as the individual stars change. It's not a fixed sculpture of light, but a living, shifting design that constantly renews itself. The galaxy's structure is complex. At its centre lies a bulge, a dense spherical region filled with old stars and orbiting clusters. Inside that bulge, hidden by dust and gas, is the galactic centre, where a supermassive black hole called Sagittarius A resides. This black hole, about 4 million times the mass of the Sun, anchors the inner region of the galaxy. It doesn't act like a vacuum, devouring everything nearby, but it exerts an enormous gravitational pull that helps shape the orbits of the stars around it. In the region close to it, stars move at incredible speeds, completing full orbits in mere decades. The closer you get to the centre, the faster the motion becomes, a swirl of gravity that defines the very heart of the Milky Way. From that core, the galaxy extends outward through its spiral arms, the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and others, stretching tens of thousands of light years. The Sun is located between two of these, in a smaller structure called the Orion Spur, a quiet, relatively stable region, about halfway from the centre to the outer edge. Here, the density of stars is moderate, the environment calm compared to the crowded inner regions. Yet even this calm is full of motion. Every star, including our Sun, is moving at hundreds of kilometres per second, orbiting the galactic centre in a vast, slow rotation that takes roughly 230 million years to complete. To imagine what that means, consider this. Since the Sun's formation, about 4.6 billion years ago, it has circled the Milky Way roughly 20 times. Each orbit marks an era not of human history, but of planetary and biological history. The rise and fall of continents, the evolution of life, the formation of mountains and oceans, the long march from simple cells to conscious beings. Each full galactic rotation encompasses millions of generations of life, and yet, to the galaxy itself, it's just one turn of an ancient wheel. The Milky Way's rotation is not uniform. Like all spiral galaxies, it exhibits differential rotation. The inner regions revolve faster than the outer ones. Stars closer to the centre complete their orbits in shorter times, while those near the edge take longer. This means that over time, the spiral arms would seem to wind tighter and tighter if they were made of fixed material. But because they are density waves, moving patterns rather than solid structures, the galaxy's form remains open and stable. The arms are like ripples on water, travelling through the medium of stars and gas, creating the appearance of a cohesive shape. Surrounding the flat disk of the galaxy is a halo, a vast, roughly spherical region that extends far beyond the visible edge. The halo contains ancient stars, globular clusters, and an even more mysterious component, dark matter. Though invisible, dark matter makes up most of the Milky Way's mass. It exerts gravity, shaping the orbits of stars and gas, but it doesn't emit or absorb light. Without it, the galaxy's stars would be moving too fast to stay bound. The fact that they remain together is one of the strongest signs that dark matter is real. The Milky Way's motion, therefore, is not just a matter of the visible stars and gas, but of the unseen substance that holds them all in place. Within this structure, everything moves relative to everything else. The stars orbit the galactic centre, the gas clouds swirl and collide, and the spiral arms sweep through the disk. Supernovae explode, sending shockwaves through the interstellar medium, compressing gas and triggering new generations of star formation. Entire star clusters drift apart over millions of years, their members becoming indistinguishable from the background of the galactic field. The galaxy is both continuous and ever-changing, a system in motion not just around its centre but within itself at every scale. The Milky Way's motion doesn't end at its own edges. It too moves through space, part of a larger collection of galaxies known as the Local Group. This group includes the Andromeda Galaxy, the Triangulum Galaxy, and about 60 smaller satellite galaxies, many of them dwarf systems orbiting the larger ones. The Milky Way and Andromeda dominate the group, and their mutual gravity binds them together. Both are moving through space at hundreds of kilometers per second relative to the cosmic background, and toward each other at about 110 kilometers per second. In roughly 4 billion years, the two will meet. When galaxies collide, they don't crash in the way solid objects do. The space between stars is so vast that even during a merger, few stars actually collide. Instead, their gravitational fields interact, distorting and reshaping each other's structures. Tidal forces stretch the galaxies into long, luminous streams of stars. Gas clouds compress, igniting waves of new star formation. Over the course of billions of years, the two galaxies will merge into one larger system, likely an elliptical galaxy. For any life that might exist on planets then, the night sky would look dramatically different, filled with vast arcs of light, new clusters, and a slow, majestic blending of two great star cities. Long before that, the Milky Way's motion continues unimpeded. It drifts toward the Andromeda galaxy, and also toward a much larger structure beyond, the Virgo cluster, a vast collection of thousands of galaxies about 50 million light-years away. Both our galaxy and Andromeda, along with other members of the local group, are falling toward the Virgo cluster, which itself is part of an even greater structure called the Virgo supercluster. These layers of motion extend outward, almost without limit, each one part of an even larger flow. At the largest scales, the Milky Way and all nearby galaxies are moving through the universe as part of a vast cosmic web, an intricate network of filaments and voids formed by gravity acting over billions of years. Galaxies are not scattered randomly. They gather along threads of dark matter and gas that stretch across hundreds of millions of light-years. The Milky Way's motion follows the gravitational pull of this web, drawn toward regions of higher density and away from the great voids that make up most of the universe. Measurements of the cosmic microwave background, the faint radiation left over from the Big Bang, show that the entire local group is moving at about 600 kilometers per second relative to this ancient light. That means the Milky Way, Andromeda, and their satellites are all drifting together through space toward a region called the Great Attractor, a concentration of galaxies and dark matter that lies hundreds of millions of light-years away. Beyond even that lies another gravitational centre, the Shapley supercluster, which continues to draw entire clusters toward it. On these scales, motion never stops. It simply merges into larger flows. The Milky Way's endless motion is not chaotic. It's governed by the same laws of gravity and inertia that shape the motion of the planets and moons. But the scale changes the experience. The forces that hold the galaxy together operate over distances so vast that even light takes tens of thousands of years to cross them. The result is a kind of slow grace, a motion that is both constant and almost imperceptible. Stars orbit silently. Clouds of gas drift and collapse. The galaxy rotates once every few 100 million years, but it never stops turning. Within that rotation, the story of the solar system unfolds. The Sun moves with its local stellar neighbourhood, a small group of stars travelling in roughly the same direction. Some of these stars, such as Alpha Centauri and Sirius, are nearby companions in this slow migration. They share a common motion, part of a larger pattern known as the local standard of rest. Even among neighbours, each star has its own peculiar motion, a slight deviation from the average. Over millions of years, these differences cause the positions of stars to shift across the sky. The constellations we know today are temporary arrangements, changing subtly over time as the galaxy's rotation carries the stars along. This slow transformation connects cosmic motion to human perception. The sky that ancient civilizations saw was not the same one we see now, and the sky seen millions of years from now will be different still. Stars that are close to us move more noticeably, while distant ones seem fixed. This creates the illusion of permanence, even though nothing in the galaxy remains where it is for long. Everything drifts, everything evolves, but so gradually that a single human lifetime captures only an instant of the movement. The Milky Way's motion also affects the environment around the Sun in subtle ways. As it travels through the galaxy, the solar system passes through regions with different densities of gas and dust. Sometimes it moves through relatively empty space, at other times it encounters denser clouds. These passages can influence the heliosphere, the bubble of charged particles surrounding the Sun, slightly compressing or expanding it. They may also affect the cosmic rays that reach Earth's atmosphere. Though these effects are minor on short timescales, over millions of years they become part of the long-term rhythm of the planet's environment. The galaxy's motion extends beyond the physical into the temporal. The stars we see now were not always there, and many of them will vanish from view as they age and die. New stars form in the spiral arms, replacing the old. The galaxy is constantly recycling itself, converting gas into stars, stars into supernovae, and supernovae back into gas. The elements forged in those explosions, carbon, oxygen, iron, are dispersed into space, where they become part of new generations of stars and planets. The very atoms in your body were once part of that cycle, born in ancient stars that lived and died long before the Sun existed. You too are part of the Milky Way's motion, your matter drawn from its endless circulation. If you could somehow perceive this motion in real time, it would look almost still. The distances are so vast and the timescales so long that movement becomes invisible to the eye. The stars would seem fixed, even though each one is moving at tens or hundreds of kilometers per second. The galaxy would seem frozen, even though it's constantly evolving. This is the paradox of cosmic motion. The greater the scale, the slower it feels, not because it actually slows, but because our perception can't grasp the immensity of the distances involved. The Milky Way's endless motion is a quiet story, one that has been unfolding for 13 billion years. It began as a cloud of gas in the early universe, collapsing under gravity and spinning as it formed the first stars. Over time, smaller galaxies merged with it, adding their stars and shaping its spiral form. Even now, the Milky Way continues to grow, consuming small dwarf galaxies and absorbing their stars into its halo. These mergers are part of its natural evolution, small adjustments in an unending process of assembly. Every rotation of the galaxy brings change, but the overall pattern remains. The spiral arms persist, the core remains dense, and the stars continue to orbit in balance. From our tiny corner of this structure, we see only a fraction of what exists, but every part of it, from the central black hole to the farthest halo star, participates in the same grand motion. The Milky Way doesn't stand apart from the universe. It is one thread in a vast interconnected fabric, moving in harmony with everything else, and as it moves, so do we, carried within one of its arms, orbiting our sun, spinning on our world, drifting with the entire galaxy through the universe. The sense of stillness we feel is the quiet of perfect motion, a balance so complete that it feels like rest. Yet beneath that calm, everything continues, every star, every planet, every atom, all following the same unbroken rhythm that has no beginning and no end, just the steady turning of the Milky Way as it moves forever onward through the cosmic sea. From our small world orbiting an ordinary star, the Milky Way seems vast enough to hold all of existence. Its billions of stars stretch so far in every direction that it feels infinite. But the galaxy, immense as it is only one among many. It belongs to a collection of galaxies bound together by gravity, drifting collectively through the deeper void. This is our galactic neighbourhood, a region of space where entire galaxies are the neighbours instead of planets or stars, each one moving on its own path, each one contributing to the slow, continuous flow of the local universe. When astronomers first began to map the sky with precision, they realised that the Milky Way was not unique. the faint smudges of light scattered among the stars, once thought to be small clouds of gas or clusters of stars within our own galaxy, turned out to be separate galaxies altogether, each containing billions of suns. The nearest of these is the Andromeda Galaxy, about 2.5 million light-years away. To the naked eye, under dark skies, it appears as a faint blur, a small, elongated patch of light. But through a telescope it reveals its true nature as a spiral galaxy not so different from our own, larger and brighter, with its own stars, planets, and possibly its own forms of life. Between the Milky Way and Andromeda lies a region filled with smaller galaxies, dwarf systems that orbit the larger ones or drift between them. Together they form what is called the Local Group, a family of more than 50 galaxies bound by their shared gravity. Most of them are small, irregularly shaped collections of stars, many less than 1,000th the mass of the Milky Way. Some, like the Large and Small Magellanic Clouds, are visible to the naked eye from the southern hemisphere. They appear as glowing patches near the constellation Dorado, close enough that astronomers can measure their motion across the sky. These two are satellite galaxies of the Milky Way, following loose, looping orbits that will eventually merge with our own galaxy. The Local Group extends roughly 10 million light-years across, with the Milky Way and Andromeda as its dominant members. Between them lies a vast, nearly empty region of intergalactic space, filled not with vacuum but with extremely thin gas and the faint background of radiation that permeates the universe. It's a quiet, sparse place, where the nearest star of another galaxy would still be millions of light-years away. To imagine that distance, think of the Milky Way as a coin. On that scale, Andromeda would be another coin placed several meters away, with space between them vast enough to hold every other object in the Local Group many times over. Despite the emptiness, the galaxies within this group are not isolated. They interact through gravity, their motions subtly linked. The Milky Way and Andromeda are moving toward each other at about 110 kilometers per second. That speed sounds enormous, but the distance between them is so great that the collision won't happen for about 4 billion years. When it does, it will not be a crash in the usual sense. The space between stars is so large that even as the galaxies merge, most stars will pass by each other unharmed. What will change are their shapes. Gravitational tides will stretch and twist them, flinging streams of stars into long arcs that may eventually settle into a single, larger elliptical galaxy. The event will last hundreds of millions of years, a slow merging of two colossal systems into one. Other galaxies in the Local Group also orbit and interact with each other. The Triangulum Galaxy, smaller than both the Milky Way and Andromeda, may play a part in that future collision, possibly merging first with Andromeda before they together meet the Milky Way. Around all three, dozens of dwarf galaxies orbit like satellites. Some are remnants of earlier mergers, their original structures torn apart by gravity. Others are small, dark, matter-dominated systems that never formed many stars. These dwarves help scientists understand how galaxies grow by accreting smaller companions over time, incorporating their stars, gas, and dark matter into larger structures. The Magellanic Clouds, in particular, are among the Milky Way's closest companions. The Large Magellanic Cloud lies about 160,000 light-years away, while the Small Magellanic Cloud is around 200,000 light-years distant. Both are irregular galaxies, meaning they lack the symmetrical spiral structure of the Milky Way. Their distorted shapes are partly the result of gravitational interactions with each other and with our galaxy. A long stream of gas known as the Magellanic Stream stretches behind them, trailing across hundreds of thousands of light-years. This gas, pulled out by tidal forces, may one day fall into the Milky Way, fueling new star formation in its outer regions. Even now, these galaxies are slowly spiralling inward, bound to merge with the Milky Way in the far future. Such interactions are common in the universe. Galaxies grow by merging, their stars and gas combining to form new generations of systems. What seems static in the night sky is actually a snapshot of a slow but continuous process of change. The shapes of galaxies, spiral, elliptical, irregular, are records of their histories, the traces of countless encounters and collisions written in their structure. The Milky Way's own spiral form was likely shaped by past mergers, including one with a galaxy known as Gaia Enceladus, about 9 billion years ago. The remnants of that ancient collision still linger in the halo of our galaxy, in the form of stars moving on elongated, tilted orbits. Our local group itself is part of a larger structure, the Virgo supercluster, which spans about 110 million light-years. Within it are thousands of galaxies organised into clusters and filaments. The Virgo cluster, near its centre, contains over 1,000 galaxies bound together by their mutual gravity. The Milky Way and Andromeda lie on the outskirts of this supercluster, drawn slowly toward its denser regions. When viewed on even larger scales, the supercluster connects to other vast structures, forming part of what cosmologists call the cosmic web. This web is the large-scale architecture of the universe, a network of filaments composed of galaxies, gas and dark matter, intersecting at dense nodes where clusters form, separated by enormous voids where almost nothing exists. Within this web, galaxies and clusters move under the influence of gravity, flowing toward regions of higher density. The Milky Way and the entire Virgo supercluster are being drawn toward a region known as the Great Attractor, about 150 million light-years away. Beyond that, an even more massive concentration of galaxies called the Shapley supercluster exerts a gravitational pull that affects the motion of thousands of clusters across hundreds of millions of light-years. Our galaxy, along with everything near it, participates in this vast migration, moving through space not randomly, but as part of an immense interconnected pattern. The motion of galaxies within the local group and beyond isn't just a curiosity. It's how we measure the expansion of the universe itself. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are receding from us, and that their speed increases with distance. This observation revealed that the universe is expanding, not because galaxies are moving through space, but because space itself is stretching, carrying galaxies apart. The local group, bound by its own gravity, resists this expansion, remaining intact even as the larger universe grows. But beyond our immediate neighbourhood, the expansion dominates. The farther a galaxy lies from us, the faster it appears to move away. The Milky Way and its neighbours drift together through an expanding cosmos, their local bonds strong enough to keep them united even as the fabric of space stretches around them. The space between galaxies isn't completely empty. It contains the intergalactic medium, a thin gas of hydrogen, helium, and trace elements heated to millions of degrees. Though sparse, it glows faintly in X-rays and radio waves. Streams of this gas connect galaxies within groups and clusters, forming the filaments of the cosmic web. As galaxies move, they exchange material with this intergalactic medium. Outflows from supernovae and active galactic nuclei push gas outward, while gravitational attraction pulls new gas inward, fueling ongoing star formation. The boundary between galaxies and the space between them is not fixed but dynamic, constantly changing as matter and energy flow in both directions. When astronomers study the local group, they often describe it as a gravitational island in the expanding sea of the universe. The galaxies within it are bound together closely enough that they will remain linked even trillions of years into the future, long after more distant galaxies have moved beyond the horizon of visibility. The Milky Way and Andromeda will merge, forming a new, larger galaxy sometimes called Milkomeda. The smaller galaxies of the local group will eventually be absorbed as well. Over immense timescales, this merged galaxy will drift alone, surrounded by darkness as the expansion of the universe carries everything else beyond reach. The stars within it will age and fade, leaving behind a quieter, colder cosmos. Right now, though, our galactic neighbourhood is alive with motion and light. The Andromeda Galaxy shines with hundreds of billions of stars, many younger and more luminous than those in the Milky Way. The Triangulum Galaxy, smaller and more delicate, glows with bright regions of star formation visible even from millions of light-years away. The dwarf galaxies shimmer faintly, some rich in gas and others nearly invisible, containing mostly dark matter. Together they form a dynamic, interconnected community of systems, each contributing its own mass and energy to the balance of the local group. Even within the Milky Way's immediate surroundings, smaller structures reveal the ongoing exchange between galaxies. Streams of stars, like faint rivers of light, arc through the halo of our galaxy, the remnants of smaller galaxies torn apart by tidal forces. These stellar streams are evidence that the Milky Way is still growing, still consuming its neighbours in a slow process of accretion. Each star in those streams was once part of a smaller system, now stretched and absorbed into the larger whole. Over billions of years, these mergers smooth out, their individual identities lost in the combined motion of the Milky Way stars. The study of our galactic neighbourhood also offers clues about the universe's invisible components. By mapping the motions of galaxies, astronomers can infer the presence of dark matter, the unseen mass that outweighs visible matter by about 5 to 1. The galaxies of the local group move as if embedded in a halo of dark matter that extends far beyond their visible edges, linking them together in a common gravitational field. Without that dark matter, the local group wouldn't exist as a bound system. Its galaxies would have long since drifted apart. The very fact that the Milky Way and Andromeda are moving toward each other, rather than away, is evidence of the strength of this hidden mass. Within this context, our place in the cosmos becomes both smaller and more connected. The Sun, the Earth, and all life here are part of a galaxy that belongs to a cluster, which belongs to a supercluster, which is part of the cosmic web that fills the universe. Every scale of structure, from the orbit of an electron to the motion of a galaxy, follows the same underlying principles of motion and gravity. The stillness we perceive on Earth is a brief pause in an ocean of movement that extends far beyond anything we can see. If you could somehow drift outside the Milky Way and look back toward it, you would see a glowing spiral hanging in the dark, with Andromeda shining nearby as another spiral of light. Between them, faint bridges of gas and scattered dwarf galaxies would fill the space. The two great spirals would appear to move almost imperceptibly toward one another, their arms slowly aligning. Around them, smaller galaxies would orbit like tiny companions following in their wake. The scale would be beyond comprehension, but the motion would be smooth, patient, and certain. A neighbourhood bound by gravity and time. All of it, the Milky Way, Andromeda, Triangulum, the dwarfs, the gas, the stars, is moving together through the universe, drawn toward distant clusters and superclusters. It's a vast system of systems, a hierarchy of motion that stretches outward without clear boundary. The galaxies that seem frozen in the night sky are part of an unbroken stream, flowing through space like leaves on a river too large to perceive from within. And somewhere inside that river, our sun drifts quietly, carrying with it the planets, the moons, and the small blue world where you sit. The stars around us are neighbours in every sense, close enough to see, distant enough to last beyond lifetimes, and all of them are part of the same vast neighbourhood. Every night when the sky is clear and the air is still, there's a faint blur above the horizon in the direction of the constellation Andromeda. It's easy to miss, a soft patch of light just barely visible to the naked eye. To most, it seems like nothing more than another cloud in the sky, or a trick of distant starlight. But that faint blur is not a star, or a cluster, or a reflection. It is an entire galaxy. The Andromeda Galaxy, our nearest large neighbour, a vast system of 1 trillion stars moving slowly through the dark toward us. Though it looks motionless, Andromeda is not fixed in the heavens. It is on a path that will one day bring it directly to the Milky Way. The two galaxies are separated by about 2.5 million light-years, an almost impossible distance to imagine. Yet despite the emptiness between them, their mutual gravity has bound them together, drawing them closer over time. Every second, Andromeda approaches at a speed of about 110 kilometers per second, faster than the speed of most satellites orbiting Earth, yet unimaginably slow when measured against the scale of cosmic distance. The motion is silent. There is no sound in the vacuum between galaxies, no wind, no current, only the steady pull of gravity. The two galaxies have been moving toward one another for billions of years, their paths set by the mass that connects them. They belong to the same local group, a family of galaxies drifting through space together, and for them, collision is inevitable. This is not a collision of solid objects, but of gravitational fields, vast diffuse structures made of stars, gas, dust, and dark matter, slowly merging through the quiet mathematics of motion. If we could watch this process unfold in real time, it would appear frozen. The approach is so gradual that nothing would seem to change over a lifetime, or even over many lifetimes. Yet over millions of years the pattern would become clear. The faint patch of Andromeda would grow brighter, its spiral shape slowly becoming visible to the naked eye. Over hundreds of millions of years it would dominate the night sky, a glowing wheel of light stretching from horizon to horizon. Its stars would no longer be distant points, but visible structures, their combined light turning the sky into a faintly luminous dome. And eventually, as the two galaxies came close enough, their halos would overlap, and the first stars from each system would begin to pass among one another. When we imagine two galaxies colliding, it's easy to picture destruction, stars smashing together, systems shattered, chaos spreading across space. But the distances between stars are so vast that almost none will actually collide. Each star, even in the densest regions, is separated from its nearest neighbour by trillions of kilometres. When the Milky Way and Andromeda meet, their stars will mostly pass by without contact. What will collide are their vast clouds of gas and dust. These clouds, when compressed by the merging gravitational fields, will trigger immense waves of new star formation. The collision will not end the galaxies, it will transform them, filling both with new generations of stars born from the turbulence of their encounter. The process will unfold slowly. Over the first few 100 million years of interaction, the galaxies will begin to distort. Tidal forces will stretch them into long luminous streams, arcs of stars drawn out by the uneven pull of gravity. Each galaxy will send out tidal tails, great bridges of starlight that connect them, while the central regions draw closer. As they pass through each other, their shapes will warp, their spiral arms torn and twisted. Then, after the first pass, they will separate again, drifting apart briefly before gravity pulls them back for another encounter. This will happen several times before they finally merge into one. The combined system that emerges will not be a spiral like the Milky Way or Andromeda are today. Over time, their ordered disks will dissolve into a single, more rounded shape, a massive elliptical galaxy, filled with old stars and long streams of gas. Astronomers have given this future galaxy a name, Milkomeda, or sometimes Milkdromeda, a simple blending of the two. It will shine brighter than either of its ancestors, with a vast halo of stars and an active centre where their black holes merge, forming one much larger black hole surrounded by swirls of hot gas. From Earth's perspective, assuming our planet still exists then, the view of the sky would be extraordinary. Long before the final merger, Andromeda would dominate the night, appearing first as a double core, two bright centres connected by hazy bridges, and then as a single enormous glow filling much of the sky. Over time, the outlines would blur as the galaxies merged fully, leaving behind a sky filled with unfamiliar constellations shaped by stars that once belonged to another galaxy. The patterns we know, Orion, Cassiopeia, the Big Dipper, would vanish, replaced by new configurations of light. but by the time this happens, billions of years will have passed. The Sun, now halfway through its life, will by then be entering its final stages. It will have exhausted much of its hydrogen fuel, grown brighter, and begun to expand toward its red giant phase. The Earth, if it remains intact, will likely no longer be habitable. The oceans will have boiled away, and the surface will be scorched. Yet even if our planet no longer supports life, the collision of galaxies will continue far above, unaffected by the fate of any single world. The universe moves on its own timescale, and its transformations unfold whether or not anyone remains to see them. Still, the story of this future merger is more than an event to come. It's part of a continuous motion that began long ago. The Milky Way and Andromeda have been moving within the same gravitational field since their formation. They both orbit the shared centre of mass of the local group, drawn toward one another by the dark matter that fills the space between them. The halos of dark matter surrounding each galaxy, enormous, invisible spheres extending far beyond their visible edges, have likely already begun to overlap. Long before the stars themselves meet, these halos interact, exchanging momentum and energy, subtly shaping the orbits of both galaxies. When the galaxies do finally merge, their central black holes will spiral toward each other in a slow, intricate dance of gravity. As they approach, they'll emit gravitational waves, ripples in the fabric of space-time itself, carrying away energy and causing the two to draw closer still. Eventually they'll collide and merge into a single, more massive black hole, perhaps tens of millions of times the mass of the Sun. The energy released in that final merger will ripple through the galaxy, a silent, invisible wave passing through every star, planet, and cloud. Although the merger will transform the structure of the galaxies, it won't destroy them. In fact, such collisions are part of how galaxies grow. The Milky Way itself has absorbed many smaller galaxies over time. The Sagittarius dwarf galaxy, the Canis major dwarf, and several others whose stars now orbit within our halo. These mergers leave behind streams of stars that can still be traced, evidence of a long history of galactic interactions. The encounter with Andromeda will simply be the largest and final major merger in that sequence. Afterward, the resulting elliptical galaxy will remain stable for trillions of years, slowly fading as its stars burn out one by one. From a scientific perspective, this event is not unusual. Throughout the universe, galaxies are constantly merging, colliding, and reshaping. In fact, it's one of the main processes through which structure evolves. Small galaxies combine to form larger ones. Clusters merge into superclusters, and over billions of years, the shapes we see now change beyond recognition. What's remarkable is that we happen to live in a moment between collisions, a rare period of calm between the major mergers that define a galaxy's life. The approaching of Andromeda also provides scientists with a laboratory for understanding galactic dynamics. By observing its motion precisely, measuring the Doppler shift of its light, tracking its proper motion across the sky, and modelling the distribution of dark matter, astronomers can predict not only when the collision will occur, but how it will unfold. Current models suggest that the first encounter will happen in about 4 billion years, with the final merger completed roughly 6 billion years from now. These predictions are based on careful measurements of Andromeda's velocity components, including a small sideways motion that determines the angle of approach. Even small uncertainties can alter the details of the encounter, but the overall outcome is certain. The two galaxies will merge. The empty space between them, though it seems void, plays a role too. It contains the intergalactic medium, a thin gas that extends between galaxies. As Andromeda and the Milky Way approach, their halos of hot gas will begin to interact, generating shock waves and heating the surrounding medium. This interaction will precede the visible collision by millions of years, marking the first sign of the coming union. Eventually, when the galaxies pass through each other, this gas will ignite bursts of star formation, lighting up the combined system with new, blue, short-lived stars that will outshine everything around them for a brief time before fading into white dwarfs. As this unfolds, the Sun and its planets, or whatever remains of them, will continue to orbit the galactic centre, drawn along by the motion of the stars around them. The probability that our solar system will collide directly with another star is extraordinarily small, but its position within the new galaxy will change. It may be flung outward into the outer halo, or drawn closer toward the centre, depending on the details of the gravitational interactions. From wherever it ends up, the view of the night sky will be completely transformed. The familiar spiral pattern of the Milky Way will be gone, replaced by a bright diffuse glow filling much of the sky, the remnant of the merged galaxies. In the long term, after the merger settles, star formation will gradually decline. The available gas will be consumed or heated, and the new galaxy will become quieter. The brilliant bursts of young stars will fade into a population of older, redder stars. The galaxy will enter a phase of slow evolution, its structure stable and its light dimming over time. The stars will continue to orbit the central mass for trillions of years, but with less activity and less change. The dynamic spiral of today will have given way to a serene, massive ellipse, a monument to billions of years of motion and transformation. Even then, the motion won't stop. The merged galaxy will continue to move through space, drawn by the gravity of nearby clusters and the larger structures of the cosmic web. The universe will still be expanding, though more slowly influenced by the dark energy that drives its acceleration. Over unimaginable timescales, galaxies beyond the local group will drift farther and farther away, their light redshifted until it can no longer be seen. The local group, now a single galaxy, will remain as one of the last islands of matter in an ever-growing sea of darkness. In this way, the journey toward Andromeda is not just an event waiting to happen in the future, it's a continuation of the same cosmic motion that has been unfolding since the universe began. Every orbit of every star, every drift of every galaxy, is part of this larger story, one of attraction, collision, and renewal. The Milky Way's slow approach toward its neighbour is simply one more expression of the universal tendency for matter to come together, to combine and reshape itself over time. If you could speed up time and watch the process play out, it would look like a slow, silent ballet. Two great spirals drifting toward each other, their arms reaching out, touching, merging, and finally settling into one. Light would ripple through them as new stars form, fade, and give way to calm. The result would be a single, luminous galaxy moving onward through space, its past written in faint streams of stars that trace the paths of the original systems. That journey is already underway. The gravitational pull that binds the Milky Way and Andromeda is acting now, imperceptibly but constantly. Every moment the distance between them decreases by a few dozen kilometres. Over the span of human history, that change is meaningless, a tiny fraction of the total distance, but over cosmic time it adds up. Millions of years from now the difference will be visible. Billions of years from now the two will be one. If you could somehow step outside the galaxy, away from the glow of stars and the swirl of its spiral arms, and look back at it from the quiet between clusters, you'd see something that most of the universe hides from view. You'd see that the Milky Way, Andromeda, and every other galaxy you can imagine are not isolated. They're connected, stretched along threads of gravity and dark matter that bind them together across unimaginable distances. The universe, though it appears empty, is woven with structure, a vast invisible web that shapes everything within it. This web is not made of light or ordinary matter. It's made mostly of something we cannot see, dark matter. Though invisible, it makes up the majority of the mass in the universe. The stars, planets, gas and dust, everything that shines or can be touched, account for less than 5% of what's actually there. The rest is hidden, detectable only through its gravitational influence. Without it, galaxies would fly apart. Without it, there would be no structure at all, no clusters, no stars, no galaxies, just scattered particles drifting forever through the dark. Dark matter reveals itself through motion. The way galaxies spin, the way clusters hold together, the way light bends around massive structures, all of these phenomena point to an unseen presence. In the 1930s, astronomer Fritz Zwicky noticed that galaxies and clusters moved too fast to be held together by the gravity of their visible matter alone. Later, in the 1970s, Vera Rubin confirmed this on a smaller scale, showing that the stars in the outer regions of galaxies rotated at nearly the same speed as those near the centre. According to Newtonian physics, that shouldn't happen. The visible mass wasn't enough to account for the gravitational pull required. Something else, something invisible, had to be providing the missing mass. Since then, every observation has deepened the mystery. Dark matter doesn't emit light, absorb it, or reflect it. It doesn't interact with electromagnetic radiation in any way we can detect. It passes through ordinary matter almost as if it weren't there, yet it exerts gravity, shaping the universe on every scale. Computer simulations of cosmic evolution show that dark matter formed the first structures in the early universe, gathering into filaments and nodes under its own gravity. Ordinary matter, gas and dust, fell into these gravitational wells, cooling and condensing to form the first stars and galaxies. The luminous universe we see today is a thin layer draped over an invisible skeleton. This invisible skeleton, the cosmic web, is vast beyond imagining. It spans the entire observable universe, stretching for billions of light years in every direction. Its filaments connect galaxies like the strands of a spider's web, intersecting at dense clusters where gravity is strongest. Between the filaments lie enormous voids, regions so empty that entire galaxies could fit inside them with room to spare. The contrast between these dense and empty regions is what gives the universe its large-scale structure, a pattern that has persisted since the earliest moments after the Big Bang. To visualize this web, astronomers use powerful simulations, feeding the laws of physics into supercomputers and letting them evolve over cosmic time. Starting from a nearly uniform distribution of matter just after the Big Bang, tiny fluctuations in density grow under gravity, forming a network of filaments. Over billions of years, these filaments merge and thicken, pulling ordinary matter into their centres, where galaxies form. When these simulations are compared with real observations, maps of galaxy positions across the sky, the resemblance is striking. The pattern of reality matches the pattern of the invisible. The structure of the cosmic web is hierarchical. On the smallest scales are stars and planets, bound into systems by gravity. On the next scale are galaxies, vast collections of billions of stars. Then come galaxy groups and clusters, containing hundreds or thousands of galaxies. These clusters are connected by filaments, which themselves are part of larger superclusters, stretching across hundreds of millions of light years. Every level is connected to the next, from the smallest orbit to the largest flow of galaxies. It's a continuum of motion, where gravity organizes matter into a repeating pattern of knots and threads. The regions between the filaments, the cosmic voids, are almost completely empty, containing only a few atoms per cubic meter. These voids expand faster than the rest of the universe because they're less dense, pushing matter toward the denser regions. Over time they grow larger, while the filaments become denser and thinner. This process gives the universe a cellular appearance, a kind of three-dimensional foam, with clusters of galaxies forming the walls and the voids forming the empty spaces in between. Even though dark matter dominates the structure, it's completely invisible to us. To study it, scientists rely on its gravitational effects. One of the most powerful tools for doing this is gravitational lensing. According to Einstein's theory of general relativity, massive objects curve space-time around them, bending the path of light. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends and distorts it, creating arcs, rings, and multiple images. By measuring these distortions, astronomers can map the distribution of mass, both visible and invisible, in the lensing cluster. The result is a ghostly outline of dark matter, a map of something that can't be seen directly, but reveals itself through the geometry of light. These maps show that dark matter doesn't clump in the same way as normal matter. It forms smooth, extended halos around galaxies and clusters, providing the gravitational framework that holds them together. In some cases, dark matter appears to interact only through gravity, not even with itself, allowing it to pass through other halos without slowing down. One of the most famous examples of this is the Bullet Cluster, two colliding clusters of galaxies observed in X-rays and visible light. The hot gas from the collision slowed down and heated up, but the gravitational mass traced through lensing passed straight through, indicating that most of the matter was invisible. This observation is among the strongest pieces of evidence for dark matter's existence. Despite decades of research, the true nature of dark matter remains unknown. It might be composed of new kinds of particles that interact only weakly with ordinary matter, or it might arise from modifications to gravity itself. Experiments deep underground, in space, and at particle accelerators all search for clues. Sensitive detectors wait for the faintest sign of a dark matter particle interacting with normal atoms, but so far nothing has been confirmed. The mystery endures, not because we lack data, but because the phenomenon is so elusive. It shapes the universe completely while remaining hidden from direct observation. The cosmic web isn't static. It evolves as galaxies move along its filaments and merge at its intersections. The flows of matter within the web continue to feed the growth of clusters and galaxies, even now, billions of years after the first stars formed. Streams of gas fall inward from the filaments, replenishing galaxies with new material for star formation. In turn, energy from stars and black holes flows outward, heating the surrounding gas and influencing the next generation of structure. This exchange of matter and energy gives the web a kind of circulation, slow, immense, and unending. The Milky Way itself lies along one of these filaments, part of a structure known as the local sheet. This sheet connects the local group to other nearby groups and clusters, all embedded within a larger filament that extends toward the Virgo cluster. On even larger scales, the local sheet is part of a region called Laniakea, meaning immense heaven in Hawaiian, a supercluster encompassing more than 100,000 galaxies spread across 500 million light-years. Within Laniakea, matter flows along gravitational valleys toward a common centre, a region known as the Great Attractor. This is our cosmic address, a map of motion and connection, showing how even our small corner of the universe is part of a network stretching across the cosmos. The idea that the universe is woven into a web changes how we think about emptiness. The spaces between stars and galaxies are not void in the true sense. They're filled with fields, particles, and the faint gravitational pull of unseen matter. Even in the quietest regions of intergalactic space, the geometry of space-time itself carries the imprint of this structure. Light from distant galaxies bends and stretches as it travels through the web, its path shaped by the invisible landscape of gravity. Every photon that reaches us carries a record of this journey. A subtle distortion, a shift in colour, a delay in time. The cosmos is not a simple vacuum but a living fabric, textured by matter and motion. When astronomers map the universe on the largest scales, they use surveys that record the positions of millions of galaxies. These maps, when plotted in 3 dimensions, reveal the filaments and voids directly. The Sloan Digital Sky Survey, for example, has created some of the most detailed views of the cosmic web ever made, showing tendrils of galaxies stretching across billions of light-years. What's remarkable is the consistency of the pattern. No matter how far you zoom out, the same general structure appears. Clusters connect to filaments, filaments to sheets, sheets to larger networks. The universe has no single centre or edge, just an endless repetition of structure within structure. In a way, the cosmic web is a record of time itself. The densest regions where galaxies and clusters now exist began as tiny fluctuations in the early universe, slight differences in density, no larger than 1 part in 100,000. Over billions of years, those differences grew under gravity, forming the vast architecture we see today. The pattern of the web tells the story of the universe's expansion, its cooling, and its evolution from simplicity to complexity. Every filament is a fossil of motion, a trace of how gravity has shaped matter since the beginning. Beyond dark matter, there is another invisible component of the cosmos: dark energy. While dark matter pulls things together, dark energy pushes them apart. It's the force behind the universe's accelerating expansion, discovered in the late 1990s through observations of distant supernovae. Together, dark matter and dark energy define the universe's large-scale behaviour. Dark matter forms the structure. Dark energy determines its fate. The balance between them decides whether the universe will expand forever, slow and collapse, or reach some steady state. Current evidence suggests that dark energy dominates, meaning the expansion will continue indefinitely. Even as the cosmic web expands, its internal structures remain bound. Gravity keeps galaxies, clusters, and superclusters intact, while the space between them grows. Over time, the expansion will stretch the web, thinning the filaments and isolating the clusters. Trillions of years from now, only the nearest structures will remain visible to one another. The rest of the universe will fade beyond the cosmic horizon, its light too redshifted to reach us. Yet the pattern of the web, imprinted in the distribution of galaxies and in the cosmic microwave background, will endure as a memory, a record of the structure that once was. The invisible web defines the motion of everything we can see. It determines how galaxies form, where stars are born, and how they move through the universe. Even the path of the Milky Way toward Andromeda is guided by the gravitational currents of this web, shaped by dark matter that neither galaxy can see but both obey. The cosmic web is not just a background structure, it's the framework of reality itself. Every particle of matter, every ray of light, every world that orbits a star moves within this web. It connects everything, from the smallest atom to the largest cluster. When we look at the night sky and see stars scattered across the darkness, we're seeing only the luminous points, the bright knots of a structure whose true form stretches far beyond sight. The universe is not a collection of isolated lights, but a single, continuous fabric, bound together by forces we cannot feel, but that shape every moment of existence. And within that fabric, the Milky Way continues its motion, drifting along one of the filaments, pulled gently toward its neighbouring galaxies, guided by the same invisible architecture that shapes the entire cosmos. The web stretches endlessly, and the galaxies within it move like beads on unseen threads, carried forward by gravity's quiet persistence. This motion has no beginning or end that we can see, only continuity, as each structure flows into the next, merging and changing but never leaving the network that binds the universe together. As the light from distant galaxies reaches us, bent and stretched by the web along its way, it tells us where we are, not at the centre, not at the edge, but woven into the middle of everything, part of the invisible structure that defines the cosmos. The motion we feel as our galaxy moves, as our star orbits, as our planet spins, is just a small vibration in that larger web, a trace of gravity's unending pull that links every world to every other in the vast, unseen architecture of space. Every motion in the universe, from the orbit of planets to the drift of galaxies, happens against a background that never changes. It's faint, uniform, and all-encompassing, a soft glow of radiation that fills every direction, everywhere, all at once. It's not light from stars, nor reflections from dust, nor the glow of any nearby source. It's the afterglow of the universe itself, the remnant heat from the moment it began. This background, called the cosmic microwave background, is the oldest light we can see. It's not just a backdrop, it's the foundation on which all motion takes place, the silent breeze that moves through the fabric of space and time. To understand what this background is, imagine the universe as it was nearly 14 billion years ago. It was small, hot, and dense, filled with particles and light tangled together in a seething plasma. In that early state, light couldn't travel freely. Photons, the particles of light, were constantly scattered by electrons, bouncing around in a fog so thick that nothing could move in a straight line. The universe was bright, but it was opaque, a glowing cloud of radiation and matter too dense for light to escape. Then, as the universe expanded, it cooled. After about 380,000 years, the temperature dropped enough for electrons to combine with protons and form neutral atoms. This event, called recombination, changed everything. With the free electrons now bound into atoms, light no longer scattered constantly. Photons could finally travel unimpeded through space. The universe became transparent, and the first light, that ancient radiation, began its journey outward. It's been travelling ever since, stretching and cooling with the expansion of the universe, until it now fills the cosmos as a faint microwave signal detectable in every direction. This light is the cosmic microwave background, or CMB for short. It's a snapshot of the universe as it was nearly 14 billion years ago, preserved in the radiation that surrounds us. To our eyes, it's invisible, because its wavelength has stretched into the microwave region of the spectrum, far beyond what we can see. But with radio telescopes, we can detect it clearly. A smooth, uniform glow that covers the entire sky with a temperature of about 2.73 Kelvin above absolute zero. It's the cold whisper of the universe's beginning, still present everywhere. The discovery of the cosmic microwave background happened by accident. In 1965, radio engineers Arno Penzias and Robert Wilson were testing an antenna at Bell Labs when they noticed a faint, persistent noise. It didn't matter where they pointed the antenna or what time of day it was, the signal was always there. They cleaned the equipment, checked for interference, even removed nesting pigeons from the antenna, but the noise remained. What they had found, unknowingly, was the echo of the Big Bang. The background radiation predicted by cosmologists as the residual heat from the early universe. Their discovery confirmed a key prediction of the expanding universe model, showing that the cosmos had indeed begun from a hot, dense state. Since then, measurements of the CMB have become increasingly precise. Satellites like COBE, WMAP and Planck have mapped it in exquisite detail, revealing not just its uniformity, but also its minute variations, differences in temperature as small as 1 part in 100,000. These tiny fluctuations are crucial because they represent the seeds of all future structure. The slightly denser regions in the early universe grew over time under gravity, becoming the galaxies, clusters and filaments of the cosmic web we see today. The CMB is, in a sense, the blueprint of the universe, an image of the moment when everything we know began to take shape. If you could see the cosmic microwave background with your own eyes, the sky would look completely different. It would not be black with scattered stars, but softly glowing in every direction, an even wash of light without shadows or boundaries. There would be no centre, because this radiation comes from everywhere equally. Every point in space sees it the same way, because it fills the entire universe. It's not something that exists outside galaxies. It exists within and around them, passing through everything, permeating every atom, every planet, every moment of space. And yet, the background is not perfectly uniform. Those tiny variations in temperature, a few microkelvins above or below average, tell us everything about the early universe. They show where matter was slightly denser, where gravity began to pull gas together, where the first stars would eventually form. The pattern of these fluctuations forms a kind of cosmic fingerprint, unique to our universe's history. When scientists analyse the spectrum of the CMB, they can measure the composition, age, and geometry of the cosmos with remarkable accuracy. It tells us that the universe is 13.8 billion years old, that it is spatially flat within a fraction of a percent, and that it is made mostly of dark matter and dark energy. The CMB also reveals something else: motion. Although the background radiation is almost uniform, we can detect a slight difference in temperature between two opposite directions in the sky. One side is slightly warmer, the other slightly cooler. This dipole pattern isn't a feature of the universe itself, it's the result of our motion through it. The Earth, the Sun, the Milky Way, and the entire local group are moving relative to the CMB at about 370 kilometers per second. Because of this motion, the radiation in the direction we're moving appears slightly blue-shifted, warmer, while in the opposite direction it appears slightly red-shifted, cooler. This effect, known as the CMB dipole, is the ultimate reference frame for motion. It defines what rest means in the universe. When we say the solar system moves through the galaxy, or the galaxy moves through the local group, or the local group moves through the cosmic web, we're describing motion relative to this background. The CMB is the fixed canvas on which all cosmic movement is painted. It's the closest thing the universe has to absolute stillness, even though it too stretches and cools with time. You could think of it as a kind of cosmic breeze, not something that pushes or drifts, but a field of light that all things move through. The galaxies don't feel it as wind, but their motion relative to it can be measured as if it were one. When scientists talk about our velocity through the universe, they're measuring it against this background. We are moving toward the constellation Leo through the CMB at hundreds of kilometers per second. The entire Milky Way carries us in that direction, and the background lights shift ever so slightly as we go, forming a subtle gradient that wraps around the sky. This background not only tells us where we are moving, but also how the universe has evolved since its birth. The light we see in the CMB was emitted when the universe was about 380,000 years old. Since then, space has expanded by a factor of roughly 100. That means the wavelengths of the original radiation, once in the visible or infrared range, have been stretched into microwaves. Every expansion of the universe stretches this light further, cooling it down. Long ago, the background glowed bright orange-white, like the surface of a star. Today, it's invisible to human eyes, and its temperature has fallen to less than 3 degrees above absolute zero. Despite its faintness, this radiation carries immense information. It contains subtle imprints left by the matter and energy the light passed through on its way to us. As it travelled across the universe, it was deflected by gravity, scattered by gas, and shifted by expansion. By analysing these tiny distortions, through a process called gravitational lensing of the CMB, scientists can map the distribution of dark matter and trace the growth of cosmic structure over time. In this way, the background light acts as a record of everything that has ever happened since its release, carrying within it the story of the universe's evolution. When you think of it, every photon of the cosmic microwave background has been travelling for almost 14 billion years. Each one left the early universe long before there were stars, galaxies, or planets. Many of them have crossed the same regions of space where new galaxies would later form. Some have passed through clusters so massive that their paths were bent. Their energy shifted slightly by gravity. By the time they reach us, they carry with them the fingerprints of all those encounters. When a radio telescope captures them, it's detecting the oldest light in existence. Light that has been moving, unbroken since the dawn of time. In a very real sense, the cosmic microwave background is the temperature of the universe itself. Everything within space, every planet, every atom, every distant star is bathed in it. Even the darkest regions of intergalactic space are not perfectly cold. They glow faintly at this background temperature. It's the baseline of all thermal energy in the cosmos. If you could remove every star, every galaxy, and every atom, the CMB would still be there, filling the void with its soft, ancient warmth. The discovery and study of this radiation have transformed cosmology. Before it was found, theories of the universe's origin were speculative. The Big Bang was one idea among many, but the CMB provided direct evidence that the universe once existed in a hot, dense state, and has been expanding ever since. It also provided a natural explanation for the large-scale uniformity we observe. The fact that distant regions of the sky look almost identical, even though they could never have communicated with each other at the speed of light. That uniformity led to the idea of cosmic inflation, a brief exponential expansion in the universe's first fraction of a second that smoothed out irregularities and stretched tiny quantum fluctuations into the seeds of galaxies. Those primordial fluctuations are preserved in the CMB as slight temperature differences. When mapped, they form a delicate pattern of spots and swirls across the sky, each one representing a region where the density of matter was slightly higher or lower than average. The size and distribution of these fluctuations reveal the geometry of space itself. They show that the universe is nearly flat, meaning its overall curvature is extremely small, and that it contains about 5% ordinary matter, 27% dark matter, and 68% dark energy. In other words, almost everything we see and experience is just a small fraction of what exists. It's strange to think that the universe's motion and shape can be read from something so faint, so quiet. The CMB is not like the light from stars which flickers and burns. It's steady and omnipresent, like the hum of an old machine still running in the background of existence. It doesn't change perceptibly from one day to the next, but it defines the reference for everything that does. All the movement, the turning of Earth, the orbit of the Moon, the drift of galaxies, happens within its glow. The CMB doesn't move through space. It is space, the residue of the universe's first light woven into the structure of reality itself. When radio telescopes capture it, what they're hearing is not a distant signal, but the universe itself, the background radiation from every direction, filling every frequency. Even ordinary televisions, when tuned to static, once captured a trace of it. A small fraction of the noise on an untuned channel comes from the CMB, meaning that a part of what flickers on an old screen is the afterglow of creation, reaching across nearly 14 billion years. The motion of our galaxy through this background also reveals our place in a broader context. The direction of the CMB dipole tells us which way we are moving through the universe. The Milky Way, along with its neighbours, is drifting toward a region of higher density known as the Great Attractor, drawn by the gravity of countless galaxies and clusters. This motion, superimposed on the quiet uniformity of the background, gives us a sense of direction in the cosmic landscape. We are moving through the fabric of space, through the oldest light, carried along by forces that have been shaping the universe since its beginning. If you could imagine yourself outside the galaxy, surrounded only by this background light, you would feel no wind, no flow, no movement, yet you would still be moving through it, through a field that's perfectly smooth in every direction, a cosmic equilibrium that only reveals motion when compared against itself. It's the closest thing the universe has to stillness, and yet it's the measure of all motion. The CMB is sometimes described as the surface of last scattering, the point in time beyond which the universe was opaque. It's the farthest we can see into the past using light. Beyond it lies the period before atoms formed, when the universe was a hot plasma of particles and radiation. To study that era, scientists rely on other signals, gravitational waves, neutrinos, or indirect traces, but light cannot carry information from before that moment. The CMB marks the boundary between the visible and the invisible history of the universe. It's the horizon of sight itself, the earliest light that space has preserved. And though that light comes from an unimaginable distance and time, it passes through us constantly. Every second, countless photons of the CMB travel through your body, through the Earth, through every atom that exists. They don't interact in any noticeable way. They simply pass through, carrying with them the memory of the universe's youth. The fact that you can exist at all, surrounded by these ancient photons, is a quiet reminder that the past is not gone. It's still here, woven into the radiation that fills space. As the universe continues to expand, the CMB will grow fainter and colder. Its wavelength will stretch, its temperature will drop, and eventually, in trillions of years, it will fade below detectability. The universe will become darker, not because the light has vanished, but because it has stretched so much that its energy is too low to be seen. Even then, it will still be there, the residual hum of the cosmos carrying on silently through the endless expansion. For now, though, it remains all around us, the quiet background to every movement. It's the light from the beginning, softened by time, stretched by space, and transformed into a whisper that fills the cosmos. Every orbit, every drift, every motion we experience takes place within that gentle glow. The cosmic background breeze that has been flowing without pause since the universe first began to expand. When you look at the night sky, it's easy to feel as though the stars are close, hanging in a dome just beyond reach. They appear as pinpoints, scattered across the same flat surface, as if they were all at a single distance from us. The truth, though, is far deeper and far stranger. The light that reaches your eyes from even the nearest stars has been travelling for years. From the more distant ones, it's been travelling for centuries, millennia, even millions of years. And from the farthest galaxies, the light began its journey before Earth itself existed. To see the universe is to look through time as much as through space, and that realization changes the meaning of distance completely. The scale of our voyage through the cosmos is so vast that normal numbers lose their meaning. We measure space not in kilometers or miles, but in the time light takes to cross it. A light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. The nearest star beyond the Sun, Proxima Centauri, lies just over 4 light years away. That's about 40 trillion kilometers. A spacecraft travelling at the fastest speed ever achieved by humans would take more than 70,000 years to reach it. Beyond that, the numbers grow so quickly that they become abstractions, too large to picture. Even within our own solar system, the scale is difficult to grasp. The Moon orbits Earth at a distance of about 384,000 kilometres, a distance that light covers in just over a second. The Sun is about 8 light minutes away, meaning that every ray of sunlight you see left the Sun 8 minutes ago. From Earth to Jupiter is about 40 minutes by light, and from Earth to Pluto more than 5 hours. The entire solar system, out to the edge of the region influenced by the Sun's gravity, spans roughly 2 light years. That means it would take light 2 years to cross the invisible boundary that separates our system from the space between stars. And yet, even that enormous space is just a small pocket within the galaxy. The Milky Way itself is about 100,000 light-years across. It contains hundreds of billions of stars, each with its own system of planets and moons. If you could travel at the speed of light, it would take 100,000 years to go from one side of our galaxy to the other. But no ship can travel that fast. The fastest human-made object, the Parker Solar Probe, moves at about 700,000 kilometers per hour. At that speed, crossing the galaxy would take roughly 200 million years. The scale of motion we exist within is beyond any personal sense of time or distance. The solar system orbits the centre of the Milky Way once every 230 million years. That means that since the age of the dinosaurs, Earth has completed just one galactic orbit. The entire history of human civilization, from the first stone tools to the present, fits into a fraction of a single rotation, less than 1/10,000th of a galactic year. All of human history has unfolded during a blink in the motion of our world around its star and its star around the galaxy. The timescales of the cosmos make every familiar measure of time seem fragile and local, like a small clock ticking inside a vast silent cathedral. The distances between galaxies are even greater. The Andromeda Galaxy, our nearest large neighbour, is 2.5 million light-years away. Its light takes 2.5 million years to reach us, meaning that we see it as it was when early humans first began using tools. The Virgo cluster, one of the nearest major clusters of galaxies, lies about 50 million light-years away. The light from those galaxies began its journey when the dinosaurs were still alive. Beyond that lies the Coma cluster, hundreds of millions of light-years away, and beyond that still are superclusters, immense gatherings of galaxies stretching across hundreds of millions of light-years. At the larger scales, the universe is arranged in filaments and voids, forming the cosmic web that extends across billions of light-years. The entire observable universe, the portion we can see, is about 93 billion light-years in diameter. That figure is not the size of everything that exists, only the size of the part from which light has had time to reach us since the beginning. Beyond that horizon, there may be more galaxies, perhaps an infinite number, forever beyond observation. The light from those regions hasn't had enough time to cross the expanding space between us. They exist in the same universe, but are permanently out of reach. Even the concept of motion changes when we think on these scales. In everyday life, motion is relative. You walk across a room, drive down a road, orbit a star. But in cosmic terms, everything moves at once. The Earth spins on its axis at about 1,670 kilometers per hour at the equator. It orbits the Sun at 107,000 kilometers per hour. The Sun, in turn, orbits the galactic centre at 828,000 kilometers per hour. The Milky Way itself moves through the local group at 2.1 million kilometers per hour, and the local group drifts toward the Virgo cluster at roughly the same speed. Relative to the cosmic microwave background, our total velocity is about 1.3 million kilometers per hour. Each of these motions adds to the next, yet none of them can be felt. We are passengers in a system of continuous movement so smooth and stable that it feels like stillness. If you were to trace all of these motions together, the spin of Earth, the orbit around the Sun, the Sun's path through the galaxy's drift through the local group, the resulting trajectory would be a complex spiral, winding endlessly through space. Each orbit overlays another, each motion nested inside a larger one. The path of a single atom in your body, when extended across time, becomes a thread in that cosmic spiral, tracing a route through the galaxy that will never repeat. You have never been in the same place twice. Every second carries you thousands of kilometers farther along a path that extends beyond imagination. The sheer size of these scales challenges the idea of place itself. On Earth, place is defined by familiar distances, meters, kilometers, maybe thousands of kilometers across continents and oceans. In the solar system, those measures expand into millions and billions. In the galaxy, light years become the only meaningful unit, and beyond that, even light years become too small. When describing the largest structures, astronomers use megaparsecs, millions of parsecs, where one parsec equals about 3.26 light years. Superclusters and filaments can span hundreds of megaparsecs, distances so vast that light takes hundreds of millions of years to cross them. From such a perspective, our world becomes almost invisible. The entire solar system is smaller than a pixel in the map of the Milky Way. The Earth itself, less than a speck. And yet, everything that has ever lived, thought, or wondered exists within that tiny space. The human mind evolved under skies it could not measure, yet it has managed to map the universe beyond its own horizon. The ability to even grasp the scale of our voyage is one of the most remarkable consequences of consciousness, the universe reflecting upon its own immensity through us. When scientists measure distances across the cosmos, they often rely on light itself as the yardstick. Light travels at a constant speed, 299,792 kilometers per second, and that constancy allows it to function as both clock and ruler. By measuring how far light travels over time, we can map the geometry of space. The redshift of a galaxy's light reveals how much the universe has expanded since that light was emitted. Each photon we receive carries the record of both distance and time, allowing astronomers to reconstruct a three-dimensional picture of the universe from the signals that reach us. The farther away something is, the older its light. Looking deeper into space means looking farther back in time, toward the moment when the first galaxies were forming, and eventually to the faint glow of the cosmic background itself. Because the universe is expanding, distance is not static. Galaxies are not simply sitting in space. The space between them is stretching. This means that the farther a galaxy is, the faster it appears to be moving away. The light from distant galaxies is red-shifted, its wavelength stretched by expansion. The relationship between distance and redshift gives us a way to measure the rate of expansion, the Hubble constant, and from that to estimate the age and size of the universe. Each new observation refines our understanding of scale, revealing a cosmos larger and older than any previous generation imagined. To appreciate these distances, it can help to compress them. Imagine the entire history of the universe scaled down to a single year. The Big Bang would happen at the first instant of January 1st. The Milky Way would form in late March. The Sun and Earth would appear in early September. Life would begin by mid-September, complex organisms in December, and all of human history, every civilization, every memory, would unfold in the final seconds of December 31st. In that same model, the distance from Earth to the nearest star would be the space between 2 grains of sand, while the nearest galaxy would be kilometers away. The observable universe would stretch beyond the borders of any map we could hold. Yet within that scale, the motions continue. Each orbit, each rotation, each drift part of the same grand pattern. When the Earth circles the Sun, it covers nearly 1 billion kilometers each year. In that same time, the solar system moves tens of billions of kilometers along its galactic path. The galaxy itself drifts hundreds of billions of kilometers through space, and the entire local group moves even farther still. Every moment, the position of every atom changes in relation to the rest. Nothing in the universe ever stays still, not even for an instant. This constant motion can be difficult to feel. The ground beneath you feels solid, the air calm. You don't feel the Earth spin or its orbit or the galaxy's drift. You see the stars fixed in place, though they are all moving. Stillness is an illusion created by balance. Every motion is matched by another motion. The speed of the Earth's rotation, for example, is balanced by the curvature of its orbit, and that balance produces the stability that allows life to exist. The stillness we experience is not the absence of motion, but the perfection of it. If you could somehow observe the Earth from far away, far enough that the entire solar system appeared as a small dot, you would see that dot moving along a curved path around the Sun, which itself follows a longer curve through the galaxy. Zoom out farther, and the galaxy becomes one of billions moving along threads of the cosmic web. From that perspective, every orbit becomes part of a larger motion, and the idea of direction loses meaning. There is no up or down, no centre or edge, only a continuous flow of matter and energy through space. The mind struggles to hold on to such scales because they exceed the range of our senses. We are built to perceive the world in meters and seconds, not light years and eons. Yet through instruments, mathematics, and the persistence of curiosity, we can extend our awareness far beyond those limits. The scale of our voyage isn't something we can feel, but it's something we can understand. That understanding transforms perspective, turning the night sky from a ceiling into an open sea. Every motion we trace, from the smallest vibration of atoms to the expansion of the universe itself, is part of the same continuum. The boundaries we draw between solar systems, galaxies, clusters, superclusters, are only markers of convenience. The reality is unbroken. The same physical laws apply at every scale. The same gravitational forces shape motion everywhere. The journey of Earth through space is inseparable from the motion of the Milky Way through the cosmic web. To know one is to glimpse the other. The scale of our voyage also reveals a paradox. The more we expand our view, the smaller we seem. But the ability to perceive that smallness, to comprehend the vastness of the cosmos, is itself something immense. Within the atoms of our bodies are particles forged in the cores of stars, scattered across galaxies, and reassembled into life that can look back and understand. The universe carries within it the capacity to know itself, and that knowledge arises here, in one of its countless corners, as a reflection of its own motion. In that sense, scale is not a matter of size alone, but of connection. Every point in the universe is part of the same continuum. There is no edge where motion stops, no fixed frame of reference outside the whole. The Earth's path through space is not separate from the galaxies, nor is the galaxies from the cosmic webs. They are different expressions of the same unfolding. Every rotation, every orbit, every drift is part of a single ongoing voyage, one so vast that it encompasses everything, and so smooth that it feels like stillness itself. The stars we see at night, scattered across distances too great to measure, are not markers of separation but traces of this unity. Each one is a beacon shining from a different point along the same web, each one a reminder that motion is not a journey from one place to another, but the continuous unfolding of the universe itself. The scale may be beyond comprehension, but it is the scale we belong to, the scale of our voyage through the endless moving fabric of space. For all the motion that fills the universe, for every orbit and drift and expansion that defines the cosmos, human life unfolds in what feels like stillness. We live our days on the surface of a spinning planet that's moving through space at incredible speed, yet we feel no wind of motion, no sense of direction, no pull that reminds us of it. To us, the ground beneath our feet is stable, the horizon fixed, the sky a quiet ceiling of stars. This stillness is an illusion, one created not by ignorance, but by balance, by the perfect regularity of motion so smooth that it disappears from perception. When you stand outside at night and look up, you're looking out from a rotating sphere, spinning eastward at over 1,600 kilometers per hour at the equator. The air moves with it, the oceans move with it, and every structure, every organism, every grain of sand moves with it. That rotation produces day and night, sunrise and sunset, yet you cannot feel it. There's no vibration, no tilt, no jolt. The spin is constant and frictionless, its direction maintained by inertia. The only evidence of it is the passage of shadows, the shift of stars across the sky, and the rhythm of time itself. From the human perspective, motion is experienced only through change in relation, the way things move relative to us, the way our surroundings shift. But on a planet where everything is moving together, motion vanishes from awareness. It becomes background, unmeasurable without instruments or thought. When you walk across the ground, you sense your movement because it differs from that of the ground beneath you. But when you move with the planet itself, the entire frame of reference moves too. There's no outside perspective to reveal the motion, and so it feels like rest. This illusion of stillness has shaped human thought for most of history. To the first observers of the sky, it was natural to imagine Earth as fixed, with the heavens moving around it. The sun rose and set, the stars turned in circles, and the moon drifted through its phases, all evidence, it seemed, of a universe revolving around a stationary world. It took centuries of observation and reasoning to reverse that view, to understand that the apparent motion of the heavens was a reflection of Earth's own rotation and orbit. Yet even now, knowing this intellectually, we still feel still. The sensation of stability is too deeply tied to our senses, to the scale at which we live. The feeling of stillness isn't limited to the ground beneath us. It extends to our sense of time. The Earth's rotation, its orbit around the Sun, and the slow turning of the galaxy are all part of a rhythm so vast that human life fits into only a brief fragment of it. The seasons change with precision. The stars return to the same positions each year, and this regularity gives us the impression of permanence. We measure time by repeating cycles, days, months, years, but the cycles themselves are part of motions that never repeat exactly. The Earth's orbit changes minutely over time. Its axis slowly precesses. Its path around the Sun drifts along with the Sun's own journey through the galaxy. What feels eternal is, in fact, constantly changing, but the change happens on scales too large for perception. The human body and mind are built to interpret motion locally. Our balance depends on the inner ear, which detects acceleration and tilt. When movement is constant and unchanging, that system stops signalling. It adapts to the motion as normal. That's why, on an airplane flying smoothly at hundreds of kilometers per hour, you can stand, read, or sleep as though you were still. The same principle applies on Earth, only magnified. The rotation of the planet is constant, its orbit stable, and our sensory systems have no way to detect such uniform motion. What remains is the feeling of calm, the quiet impression that the world beneath us is fixed. In a way, this perception of stillness is essential for life. If we could feel every motion the Earth makes, its spin, its orbit, its galactic drift, existence would be unbearable. The subtle constancy of motion creates the conditions for rest, for continuity, for the sense that we can pause even when nothing in the universe truly stops. Stillness is the experience of perfect motion. Motion so even and balanced that it creates the illusion of peace. This sense of stillness also shapes how we experience the sky. When you look up, the stars appear unmoving, their positions fixed in patterns that repeat year after year. But in truth, every star is moving through space, orbiting the centre of the galaxy, each on its own path. The constellations we recognise are temporary arrangements, slowly shifting over tens of thousands of years. The North Star, which now marks the axis of Earth's rotation, will not always do so. As Earth's axis precesses, it will trace a circle in the sky over 26,000 years, pointing to different stars in succession. Yet across the span of a single human life, none of this movement is visible. The heavens seem eternal because our lives are short compared to the timescales of change. This disparity between perception and reality creates a paradox. We are surrounded by motion on every scale, planetary, stellar, galactic, and yet we experience almost none of it directly. Our senses evolved for survival in a narrow range of experience, attuned to movement we can respond to, indifferent to motion too vast or too slow to matter in daily life. That gap between the world as we feel it and the world as it is lies at the heart of the human sense of stillness. It's not ignorance but perspective, a reflection of how life has adapted to stability in the midst of motion. If you were to leave Earth and drift into orbit, the illusion would begin to break. From space, the planet's rotation becomes visible. Continents moving beneath clouds, sunrise sweeping across oceans, night advancing over cities. The curve of the horizon reveals the planet's shape, and the stars no longer rise or set but remain fixed as the Earth turns. The motion becomes clear only when viewed from beyond the system that defines your frame of reference. The same is true for the solar system itself. From a distance, you could watch the planets circle the Sun, each following its own elliptical path. From farther still, you could see the Sun and planets together moving through the Milky Way. But from within any one of these systems, the motion feels like stillness, because everything around you moves in concert. That principle extends outward indefinitely. Within the galaxy, the stars share a common rotation. Within clusters, galaxies drift together. Even on the larger scales, the cosmic web itself expands uniformly. At every level, motion appears still to what moves within it. Stillness, then, is not the absence of motion, but the perfect synchronization of it, the state in which everything moves together, and therefore nothing seems to move at all. The human sense of stillness is reinforced by the environment we inhabit. Gravity binds us to the Earth's surface, anchoring our bodies and our senses to the same reference frame. The air moves with the planet, the oceans move with it. Even the atmosphere's rotation is synchronized to some degree with the planet's spin. This coupling isolates us from the larger motions around us. The forces that keep us grounded also keep us unaware. We exist inside a cocoon of stability created by gravity and inertia, and that cocoon shields us from the turbulence of cosmic motion. Yet, through understanding, we can step beyond that illusion. When we learn how fast we move through space, when we calculate the speeds and distances, when we look through telescopes and see the light from distant galaxies shifted by motion, the stillness we feel becomes part of a larger perspective. It doesn't vanish, but it changes meaning. It becomes not ignorance but harmony, the calmness of being carried along perfectly by forces vast enough to include us completely. On the most immediate level, the feeling of stillness is what allows us to rest. When we lie down, close our eyes and let our thoughts quiet, we sink into the same steady motion that carries the Earth through space. The pulse of the body slows, the mind drifts, and though the planet continues to spin beneath the stars, it feels as though everything has stopped. In that moment, our internal rhythms align with the rhythms of the world around us, the turning of the Earth, the cycle of light and dark, the gravitational balance that holds oceans and atmosphere in place. Sleep, in that sense, is not a break from motion, but an immersion in it. The stillness we feel at rest is the body's recognition of balance with the moving world. There's also a psychological dimension to this stillness. Human thoughts seek stability. We build calendars, clocks, and maps to make sense of time and place. We crave repetition and order, even as everything around us changes. The daily cycle of sunrise and sunset, the phases of the moon, the return of the seasons, all of these patterns create a sense of continuity. They are the visible aspects of deep emotions that we can't feel, translated into forms we can live by. Stillness becomes the experience of patterns so reliable that they define the boundaries of awareness. But our perception of stillness isn't absolute. It shifts with context. On a windy day, the trees move but the mountains don't. From an airplane, the ground moves but the sky seems still. From space, the Earth moves but the stars do not. The sense of what's still and what's moving depends entirely on where we stand. There's no fixed reference, no ultimate frame of rest. What feels stationary from one perspective is in motion from another. Even the cosmic microwave background, the closest thing to an absolute frame, is itself changing, cooling as the universe expands. Stillness is always relative, always part of a larger movement. Yet that relativity doesn't make stillness meaningless. If anything, it gives it depth. The fact that we can experience peace, balance, and calm in a universe of ceaseless motion shows that stillness isn't a property of space, but of perception. It's the mind's ability to find equilibrium within motion, to feel at home inside change. The human sense of stillness, then, is not a mistake. It's a form of adaptation, a way of living comfortably in a moving cosmos. In this way, stillness and motion are two sides of the same reality. The universe moves, but it moves smoothly. Its laws are consistent, its patterns continuous. We move within it, and because we move as part of it, we feel still. The stars wheel overhead, the planet spins beneath us, the galaxy drifts through the cosmic web, and all of it happens in perfect, unbroken silence. The absence of sensation is not the absence of movement. It's the presence of balance. When you stand outside under a clear sky, breathing in the night air, you are part of that balance. You're on a rotating planet orbiting a star carried through a galaxy that's moving through the universe. You're in motion through time and space, but you feel no motion at all. That stillness is real, not as an absence of change, but as the harmony of all change combined. It's the calm of being carried within a system that moves perfectly, without friction or sound, through a vast and endless cosmos. And somewhere in that quiet, in that balance between motion and perception, lies the very thing that makes awareness possible. The sense of stillness is not a flaw in understanding. It's the state that allows thought to exist, reflection to happen, and wonder to arise. It's the still point from which we can look outward and grasp the motion of everything else. The Earth moves, the stars move, the galaxy moves, and yet we can pause within that movement and see it for what it is. That pause, that feeling of calm in the midst of motion, is as much a part of the universe as the motion itself, the human sense of stillness within the endless flow of the cosmos. Motion is everywhere, and it has been since the first moment the universe began. It is the quiet principle behind everything we see, the way stars form, the way galaxies turn, the way light travels, and even the way time unfolds. Every atom moves, every wave of energy moves, every force acts across a changing distance. To exist is to be in motion. The stillness we feel is only the balance of these motions, an equilibrium so complete that it gives rise to calm. Yet beneath that calm, the universe flows continuously. If there's poetry in the cosmos, it lies not in words or rhythm, but in that flow, in the ceaseless movement that connects everything. When we think of motion, we often imagine it as something that happens in space. A planet orbits a star, a comet crosses the solar system, a galaxy spins on its axis. But motion is not limited to the movement of things through space. Space itself moves. It stretches, expands, and changes with time. The galaxies are not racing through a fixed background. The background itself is growing. The distances between galaxies increase not because they're flying apart, but because the space between them is stretching. This expansion carries everything with it, like dots on the surface of an inflating balloon, each one moving away from every other as the surface grows. On that scale, motion isn't a journey from one place to another. It's a continuous transformation of the fabric that defines place itself. The laws that describe motion, the principles of inertia, acceleration, and gravity, are simple, but their consequences are profound. They shape the structure of the cosmos from the smallest particles to the largest clusters. In Newton's time, motion was seen as something that required a cause, a force to start it, a force to change it. But Einstein's theory of relativity revealed something deeper. Motion isn't only about objects moving through space, it's about the geometry of space-time itself. Mass and energy curve that geometry, and the motion we see, the orbits of planets, the fall of light near stars, follows those curves naturally. What we call gravity is not a force in the usual sense, but the shape of motion through curved space. The poetry lies in that geometry, in the way matter tells space how to curve and space tells matter how to move. Every motion in the universe follows this mutual relationship. The Earth orbits the Sun because space-time around the Sun is curved by its mass. The Moon orbits Earth for the same reason. On a larger scale, galaxies orbit the centres of clusters, and clusters drift within the gravitational wells of superclusters. Every orbit, every drift, every expansion is an expression of the same fundamental principle, the curvature of space-time guiding motion. The same equations that describe the fall of an apple describe the paths of galaxies across billions of light years. In that sense, the universe has an internal coherence, a consistency that gives rise to its beauty. The same rules apply everywhere, regardless of scale or place. The physics that governs an atom in a laboratory also governs the movement of stars in the galactic core. The constants of nature, the speed of light, the strength of gravity, the charge of the electron, are the same in every corner of space we can observe. This uniformity allows motion to be predictable, but also endlessly varied. From those simple ingredients, infinite complexity emerges. Consider the motion of light itself. It moves not because something pushes it, but because motion is its very nature. Light is constant. It travels at the same speed for every observer, regardless of their own motion. That constancy defines the structure of time. It means that when you move faster, time slows for you. When you're near a massive object, time slows for you. Motion and time are inseparable, woven into a single continuum. The way we move determines how we experience the passage of time, and the way time flows determines how we move. Every step, every orbit, every cosmic expansion happens within that single interwoven system. From this perspective, motion becomes something more than change of position. It becomes the unfolding of existence itself. Each moment is a new configuration of the universe's motion. Particles arranged differently, forces interacting anew, energy shifting from one form to another. Nothing ever stops completely. Even in the coldest, darkest regions of space, where the temperature hovers just above absolute zero, particles still vibrate slightly, retaining what physicists call zero-point energy. Absolute stillness, the complete cessation of motion, does not exist. The universe continues to move even in its quietest states. This persistence of motion is the reason why time cannot reverse itself. The second law of thermodynamics, the principle that entropy or disorder tends to increase, gives motion direction. The arrow of time points forward because energy spreads out, because motion disperses rather than concentrates. Every event leaves a trace. Every change creates an irreversible record. The flow of motion through time is the process by which the universe evolves, and its one-way direction defines the meaning of before and after. In this sense, time is the poetry of motion written into the structure of the universe. When you consider all these layers together, the motion of particles, the motion of planets, the motion of galaxies, and the expansion of space itself, what emerges is not chaos, but a pattern of extraordinary balance. The equations that describe this balance are elegant, not because they are simple, but because they capture something fundamental about how the universe organizes itself. Even turbulence, even the apparent randomness of motion on smaller scales follows deeper laws of order. The flow of air over wings, the swirl of clouds in an atmosphere, the drift of stars through a galaxy, all are governed by the same principles of energy and momentum. What we perceive as disorder is often just complexity too great for the eye to resolve. This same motion gives rise to structure. Galaxies form from clouds of gas drawn together by gravity. Stars form within galaxies as those clouds collapse. Planets form around stars from disks of dust and ice, their orbits shaped by the balance between gravitational pull and momentum. Even on Earth, motion builds and transforms. The rotation of the planet drives winds and currents. The movement of tectonic plates reshapes continents, and the flow of water carves valleys and deltas. On every scale, motion is the architect of form. Within living systems, motion takes on new meaning. It becomes the basis of metabolism, the flow of energy that sustains life. The molecules in your cells vibrate, collide, and rearrange constantly. The blood in your veins moves in pulses driven by the rhythm of your heart. The air you breathe cycles in and out, exchanging gases that fuel every reaction in your body. Even your thoughts depend on motion, the flow of electrical impulses through neurons, the chemical movement across synapses. Consciousness itself is a pattern of motion within matter. When you think, you're participating in the same physics that moves stars, only at a different scale. The human body is a small universe of motion, an organized system maintained by balance. Every beat of the heart, every breath, every neural signal is a repetition of the same cosmic principle: equilibrium in motion. Life exists not in opposition to motion, but because of it. If the universe were truly still, no energy could flow, and without flow, there could be no processes, no change, no life. Existence depends on movement. The calm we experience is the calm of dynamic stability, a harmony of countless motions that cancel one another's extremes, leaving behind the sensation of peace. When people describe beauty in motion, a wave breaking, a planet rising, a dancer turning, what they're recognizing, often unconsciously, is this deeper harmony. The elegance of motion arises from balance, from the interplay between inertia and force, between freedom and constraint. It's the same principle that keeps planets in orbit. Forward motion balanced perfectly against gravitational pull. The same pattern appears in everything from the swing of a pendulum to the curvature of a galaxy's spiral arm. The universe expresses its symmetry through motion, and the human mind, attuned to symmetry, perceives that expression as beauty. This sense of beauty also comes from our ability to recognize patterns across scales. The motion of clouds in the sky and the motion of galaxies in deep space follow the same general dynamics. The shapes of river deltas and the filaments of the cosmic web share similar branching forms. These resemblances are not coincidences. They arise from the mathematics of flow, from the way systems evolve when energy moves through them. Nature repeats its patterns across size and time, and we recognize those repetitions instinctively. The poetry of motion is written in those patterns, visible wherever matter moves and reorganizes itself. Even in apparent stillness, motion continues quietly. A stone resting on the ground seems unmoving, yet its atoms vibrate with thermal energy. The light falling on it changes with the position of the sun, the shadows shift, the air around it stirs with microscopic currents. Over time, the stone weathers, erodes, and returns to dust. The solid surface of the earth itself flows slowly under immense pressure, continents drifting on molten rock. Nothing in the physical universe is ever truly static. Time guarantees motion, and motion guarantees change. There's a kind of humility in realizing that motion never stops. It means that every moment, every configuration of matter is temporary. The mountain ranges we call eternal are rising and eroding at the same time. The stars we see as constant are burning through their fuel, destined to fade or explode. Even the atoms that make up our bodies will eventually disperse into space, recycled into new stars, planets, and life forms. The universe doesn't rest, and we are part of its continuous transformation. This continuity connects the smallest with the largest. The motion of electrons in an atom and the rotation of galaxies follow the same mathematical patterns of energy and balance. When you trace those patterns outward, you find that everything is part of a single, ongoing flow. The orbits of planets mirror the orbits of electrons in some ways, both governed by central forces. The oscillations of stars, the vibrations of molecules, the waves of the ocean, all are expressions of energy seeking equilibrium. Motion is the universal language of change, and everything speaks it. In human culture, motion has always fascinated because it symbolizes both life and impermanence. The flowing river, the turning wheel, the circling stars, all serve as metaphors for time and transformation. But beyond metaphor, motion is the literal structure of existence. When you watch a wave roll toward the shore, you're witnessing the transmission of energy through water molecules that barely move from their places. The wave's motion is real, but the water's motion is limited, an elegant example of how movement and form coexist in harmony. The same principle applies at every scale. The stars in a galaxy orbit within a collective pattern, their individual paths contributing to a structure that seems stable even as it moves. The poetry of motion lies in that paradox: change that creates permanence, movement that sustains form. There's another kind of poetry in the predictability of motion. the orbits of planets, the rotation of stars, the oscillations of light, all can be described by equations that remain constant across time and space. Those equations are not inventions but discoveries, reflections of the universe's internal consistency. They allow us to predict eclipses, tides, seasons, and cosmic events billions of years in the future. The reliability of motion is what makes science possible, and its regularity gives meaning to the concept of time. Without consistent motion, there could be no rhythm, no memory, no anticipation. Yet the universe is not perfectly regular. Within its laws, there is room for chaos, for complexity, for unpredictable outcomes that arise from small variations. The same motion that creates order also allows for surprise. The turbulence of air, the flicker of fire, the orbit of asteroids all follow deterministic laws, yet their precise paths can't be known far in advance. This balance between order and unpredictability gives motion its richness. The universe is not a clockwork, but a living system of flows and feedbacks, where stability and change coexist in perpetual interplay. To live in such a universe is to be part of that interplay. Every breath you take is an exchange of energy with the cosmos. The oxygen in your lungs came from stars that exploded long before the Earth formed. The carbon in your body was forged in stellar cores. Every step, every heartbeat, every thought is powered by processes that trace back to the same thermodynamic principles that govern the birth of galaxies. You're made of motion, sustained by motion, and destined to return to it. When you stand still, when you pause and feel your own breath, you're not stopping motion, you're aligning with it. The blood continues to flow, the atoms continue to vibrate, the earth continues to turn. Stillness, in this sense, is not the absence of motion, but the awareness of balance within it. The poetry of motion is not just out there in the stars or the tides, it's in the way we exist at all, carried forward by forces we can barely comprehend. If the universe had a language, motion would be its grammar, the way it constructs reality from energy and form. Every phenomenon we observe, every structure that endures, every change that unfolds is an expression of that grammar. The stars burning, the galaxies rotating, the expansion of space, the flicker of neurons, all of it is motion, shaped by laws that allow both stability and evolution. To recognize this is to see the universe not as a collection of objects, but as a continuous process, a flow of energy transforming endlessly. The poetry of motion, then, is not in what moves, but in what motion creates. The patterns, the rhythms, the continuity. It is the quiet narrative of existence unfolding through time, a story told not with words, but with the movement of everything that is. From the spin of atoms to the drift of galaxies, it's the same story repeated at every scale, never ending, never repeating exactly, always changing, always flowing forward into what comes next. Everything moves, but there is no final motion. There is no moment when the universe stops, and no point where it truly begins again. There is only continuity, an unbroken unfolding of change through time, so steady that it feels like silence. When we step back far enough to see all the layers of movement together, from the smallest trembling of particles to the rotation of galaxies and the expansion of space itself, what we find is a single, continuous motion, without pause or edge. This is the quiet continuum, the calm within all motion, the underlying state of everything that exists. It's not a metaphor or an idea. It's the simple physical reality of a universe that never stands still. From the earliest moments after the Big Bang, every particle has been in motion, every field fluctuating, every region of space changing in relation to every other. That movement didn't begin in time, it created time. The expansion of space, the flow of radiation, the formation of matter, all of it are expressions of the same continuity, the same dynamic fabric of existence that has no gap, no still frame, no frozen instant. When we try to imagine the end of motion, what we really imagine is the end of change, a world where nothing evolves, where time has stopped. But such a world cannot exist in the physical sense. Even at absolute zero, even in the deepest void between galaxies, motion persists at the quantum level. Particles fluctuate in and out of existence. Virtual fields shift and oscillate. The vacuum itself is alive with subtle activity. The stillness of space is not an absence of motion, but its most balanced state. Motion so symmetrical, so evenly distributed, that it feels like peace. The quiet continuum is not static. It flows through everything, shaping and reshaping, sometimes gently, sometimes violently, but always in accordance with the same laws. Galaxies collide and merge. Stars are born, live and die. Atoms combine and separate. Particles decay and reform. Each transformation is local, brief, and finite, but all are connected through the same uninterrupted process that has been unfolding for billions of years. If there is an ultimate pattern to the universe, it is not the pattern of repetition, but of unending evolution, an ongoing continuity of change that encompasses all things. From our human vantage, continuity is what gives the universe its coherence. The sun rises each day because the earth keeps turning. The stars remain visible because their light continues to travel. The universe expands because its energy keeps flowing outward. But on a deeper level, continuity is not about repetition, it's about persistence. The motion that began at the dawn of time hasn't stopped once since. Every process in nature, every orbit, every cycle, every vibration is a small part of that same continuum, an expression of energy never lost, only transformed, the idea that energy is conserved, that it cannot be created or destroyed, only changed in form, is one of the simplest and most powerful truths in physics. It's also one of the most profound. It means that nothing ever truly disappears. The energy of stars becomes the light that travels through space, the heat that warms planets, the chemical potential that drives life, and eventually the radiation that fades back into the cosmic background. The cycle continues, not in circles, but in a constant flow from one form to another. Matter and energy are interchangeable. Their transformations are the heartbeat of the universe. The continuity extends through scales of space and time beyond anything we can intuitively imagine. The atoms in your body were once part of stars that lived and died billions of years ago. The calcium in your bones was forged in supernovae, the iron in your blood in the cores of massive stars, the oxygen you breathe in the fusion reactions of stellar nurseries. Those atoms have travelled across the galaxy, through interstellar clouds, through the long chain of generations of stars, before becoming part of a living organism on a small planet orbiting an ordinary star. When your body eventually returns to the Earth, those same atoms will continue their journey into soil, into air, into other forms of life. Continuity doesn't just exist in the cosmos, it passes through us. This seamless flow of matter and energy connects every scale of existence. The same gravitational pull that guides galaxies guides the fall of a leaf. The same electromagnetic force that binds atoms together creates the light of stars. The same quantum fluctuations that fill the early universe still ripple through the vacuum of space. There is no dividing line between large and small, between cosmic and human. The continuum is unbroken, and we are part of it, living patterns of motion sustained by the same physics that governs everything else. Even death, when viewed through this lens, is not an end but a transition. The forms that life takes are temporary, but the matter and energy that compose them continue. The universe is full of such transitions. Stars burn through their fuel, collapse and scatter their elements, giving rise to new generations of stars and planets. Planets change, atmospheres evolve, life adapts. At every scale, endings feed beginnings, and beginnings are just new configurations of the same unbroken process. The continuum ensures that nothing is lost, everything is reabsorbed into the larger flow. The quiet of this continuity lies in its scale. From within, it seems like stillness because it's too vast and smooth to feel. Just as the Earth's rotation is imperceptible because everything around us moves with it, the universe's continuity feels calmer because it includes everything. There is no external frame of reference from which to see it change. The expansion of space, the passage of time, the transformation of energy, all occur together, leaving no contrast to measure against. The silence of the cosmos is not emptiness, but total inclusion. Even the ultimate fate of the universe, whatever it may be, is part of this same continuum. If dark energy continues to drive accelerated expansion, galaxies will drift farther apart until their light can no longer reach one another. Star formation will slow, then stop. The stars that remain will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even those will decay, evaporating through processes like Hawking radiation. The universe will cool, fade, and approach a state of maximum entropy, a uniform cold expanse filled with faint radiation and the remnants of matter. That vision, sometimes called the heat death of the universe, is not a destruction, but a settling, the ultimate equilibrium of all motion. Even then, continuity persists. The radiation still travels, the fabric of space-time still exists, and the quantum fields that underlie reality still fluctuate. The quiet at the end of time is not an absence of motion, but its smoothest possible form, the final symmetry where everything moves together at the same pace. The continuum remains, as calm and complete as it was in the beginning. This understanding doesn't make the universe less alive, it makes it more astonishing. To realize that everything, including thought and feeling, emerges from this continuous movement gives depth to every moment of experience. When you breathe, the air that enters your lungs has been circulating through the planet for billions of years, exchanging atoms with oceans, rocks, and other living beings. The photons that reach your eyes when you look at the night sky have been travelling through space since long before the Earth existed. The water in your cells has passed through comets and clouds, through countless generations of cycles. You are the latest arrangement in an unbroken chain of transformations that began with the birth of the universe. Every action, every thought, every heartbeat contributes to this continuity. The energy you use to move or think comes from the sun, which in turn draws its energy from nuclear fusion, powered by the gravitational collapse of hydrogen clouds that formed billions of years ago. That energy, once spent, radiates outward, warming the air, feeding plants, returning eventually to the Earth and to space. There is no boundary where your motion ends and the universe's begins. The quiet continuum flows through you, invisible but constant, defining every process of your existence. What we call awareness, the experience of being, is itself a momentary configuration within this flow. The brain's activity, the patterns of neurons firing and interacting, is another layer of motion shaped by the same physical principles. Consciousness doesn't exist outside of the continuum, it's part of it, emerging naturally from the organization of matter and energy. The fact that the universe can generate beings capable of reflecting on its motion is not an accident. It's the result of the same laws that make stars shine and galaxies turn. In that sense, awareness is the universe recognizing its own continuity, seeing itself in motion from within. If you were to imagine the universe not as a collection of objects, but as a single process, a wave, a current, a continuum, you'd find that there are no true separations, only gradients. Galaxies fade into intergalactic gas, which fades into the cosmic background. Matter dissolves into energy, energy into radiation, radiation into expansion. Everything transforms smoothly, without abrupt edges. Even the concept of a beginning, the Big Bang, is not necessarily a singular start, but a boundary in time beyond which our current understanding cannot see. The continuum may have no beginning or end in the way we think of them, only transitions between states. The quiet of this process comes not from slowness, but from balance. Every motion is countered by another motion. Every force is met with resistance. Every wave is matched by its echo. The result is not chaos, but a deep equilibrium that spans all scales. When we sense peace in nature, the stillness of a calm sea, the silence of a clear night, the steadiness of the horizon, what we're feeling is alignment with that balance. The Earth's rotation, the orbit of the Moon, the pull of gravity, and the expansion of space all combine to create a world that feels stable. The tranquility we perceive is not separate from the universe's motion. It is that motion, harmonized and continuous. To live within this continuum is to be both transient and eternal. Every form changes, but the process continues. Every life ends, but the energy and matter persist. Every star fades, but its light travels on, adding to the cosmic background. Continuity means that nothing is ever truly isolated or lost. It is all part of the same unbroken field of motion. When one system dissolves, its components become part of another. The dust of old stars becomes the material of new planets. The remnants of living beings become part of future life. The continuum preserves everything, not as static memory, but as ongoing transformation. The awareness of this continuity brings a kind of serenity. To recognize that the universe doesn't stop, that its motion includes you, that your existence participates in its flow, can transform the way you perceive both time and self. The moments that pass are not losses but transitions. The future is not a destination apart from the present. It is the continuation of the same unfolding. The quiet continuum means that you have never been outside the flow of the universe, not for an instant. Every thought, every breath, every heartbeat has been part of the same motion that began with the first expansion of space. When you lie still, breathing gently, you're moving with the earth as it turns beneath the stars. The air that passes through you connects you to the atmosphere, the planet, the galaxy, and beyond. You're not a passenger on this journey. You're a pattern within it, one that emerges for a time and then transforms. The calm you feel when you rest, when you let the mind settle, is the same calm that exists at the heart of all motion. The equilibrium of forces so vast and balanced that they give rise to stillness. The universe has no edge and no pause. Its expansion continues, its structures evolve. The same motion that began in the first light continues now, unbroken, through every particle, every wave, every living being. The quiet continuum carries everything forward, not in haste, not in chaos, but in perfect steadiness. It is the flow beneath all things, the silent foundation of existence itself, the motion that never began, that never ends, that simply is, always and everywhere, the calm and unending movement of the universe.